Hi everyone, welcome to Go Classes. In this lecture, we will study input-output data transfer techniques. In this lecture, basically, we need to study three techniques for input-output data transfer. That is, one technique is programmed I/O, another is interrupt-driven I/O, and another is direct memory access. That is DMA. So, in this lecture, let me tell you that we will study programmed I/O and interrupt-driven I/O. In this lecture, these two techniques we are going to study. So before we study these techniques for IO data transfer, let me ask you one question that when I say IO data transfer, then this data transfer happens between which devices? Please tell me. See, my question is data transfer between whom? In your computer, you have CPU, there is main memory, there are IO devices. Now, when we say that IO data transfer, then this data transfer happens between whom? And the answer is between memory and IO devices. Okay, so don't think that data transfer happens between CPU and IO devices. No, data transfer happens between memory and IO devices. Is this clear? Let me know. So remember, there is, you know, that in your computer, in your system, there is CPU. Okay, there is main memory. This is your main memory, and there is IO devices, right? Okay, so this is our IO device. Now, when we say data transfer, IO data transfer, then basically we talk about data transfer between main memory and IO devices. Okay, so this is what we need to study, that how can we do data transfer between main memory and IO devices. So this data transfer we need to study. Okay, is this clear? So very simple. Now let me tell you one thing, that most of the time, or I can say that in these two techniques, programmed IO and interrupt driven IO, in these two techniques, actually, this data transfer happens via CPU. Okay, so if you want to do data transfer between IO and main memory, then this data transfer will actually happen via CPU. Means, for example, if you want to do data transfer from IO to main memory, then what will happen? First, this data will be loaded in CPU, then it will be stored in main memory. Similarly, if you want to do data transfer from main memory to IO, then what will happen? First, this data will be loaded in CPU register, then this data will go to the IO. Okay, so remember, this data transfer we need to study, but this data transfer will happen via CPU in these two techniques. Okay, and in DMA, the name itself is telling you direct memory access. So in this DMA, in this third technique, the data transfer will happen directly. Okay, between main memory and IO devices, the data transfer will happen directly without any intervention of CPU. Okay, so very simple. So remember, here when we say data transfer, then this data transfer between main memory and IO devices. Okay, so between whom, and what is the answer? Between whom? The answer is main memory and IO devices. Okay, so you can easily see here that we want to do data transfer between IO devices and main memory, and for this we have three methods. One is programmed IO, another is interrupt driven IO, and another is DMA. Okay, and let me tell you that in these two methods, what happens? In these two methods, we do data transfer. So here, for example, you have IO device, we want to do data transfer from IO device to main memory, or from main memory to IO device. But remember, this data transfer will happen via CPU. Okay, via CPU means this is your CPU. So if I want to do data transfer from IO to main memory, then what will happen? So remember, this data transfer will happen via CPU. Means you can think like this, that it will happen like this. Okay, so we are transferring the data between these two, but it will happen via CPU. Okay, in these two techniques. And in this technique, what will happen? In this DMA, in this technique, the data transfer will happen directly without any intervention of CPU, or I can say with very less intervention of CPU. Okay, so here you can see IO and main memory, the data transfer will happen directly. Okay, is this clear? Please tell me, did you understand? Okay, so in these two techniques, programmed IO and interrupt driven IO, in these two techniques, basically this CPU is working as the middleman. Okay, this CPU is working as the middleman. As the middleman means, if you want to do data transfer from IO to main memory, then what will happen? First, the data will go to the CPU. Okay, means first the data will be loaded to CPU, then this CPU will store in the main memory. Okay, and similarly, if you want to do data transfer from main memory to IO, then what will happen? First, the data will go to CPU, then the data will go to the IO. Okay, so this CPU is working as middleman in these two techniques. Okay, and in this direct memory access, the name itself is telling you direct memory access. Here the data transfer between IO devices and main memory, this will happen directly without any intervention of CPU, or I can say with very little intervention of CPU. Okay, so very simple. Now in this data transfer, what are the challenges? What are the challenges in this data transfer? Okay, I told you that we want to do data transfer between IO and main memory, but this will happen via CPU. Okay, this will happen via CPU. So you can create the diagram like this. So it will happen via CPU. Okay, now what are the challenges in this data transfer? So let me tell you the challenges. The challenges are like this. See, CPU and main memory, they are very fast. Okay, but IO devices, they are very slow. Yes or no? So you can notice the data transfer rate of IO devices, that is usually very slow than comparing to CPU and main memory. Okay, so CPU and main memory, they are very fast. These two devices, CPU, main memory, their data transfer rate is very fast. But this IO device, this is very slow. Okay, so we need to handle this challenge. Yes or no? So this is one issue. We need to handle this issue. Okay, is this clear? For example, let me give you one concrete example. Consider this situation that there is a keyboard. IO device is, let's assume that is a keyboard. Okay, so this is your IO device. This is the keyboard. And let's assume we want to do data transfer from keyboard to main memory, and there is CPU. Okay, here you have CPU, and here you have main memory. Now what we want to do, we want to do data transfer from keyboard to main memory. I told you this data transfer will happen via CPU. Yes or no? So this data transfer we want to do, but this will happen via CPU. Okay, first the data will go to CPU, then this data will go to the main memory. Okay, let's assume I want to do data transfer from keyboard to memory. This is what I want to do. Okay, from keyboard to main memory, this data transfer I want to do. Now notice one thing. What is the speed of keyboard? Let's assume you are very fast. Okay, you do a lot, very fast typing you can do. Then in 1 second, how many characters can you type? Tell me. In 1 second, you are very fast typer. Okay, as a user you can do very fast typing. Then tell me, once in 1 second, how many characters, how many buttons can you press? Okay, so I can assume, let's assume 10 buttons. Yes or no? Okay, so let's assume that you can press 10 keys, you can press. Now 10 keys means that is 10 characters. Yes or no? That is 10 characters. That is 10 characters. 10 characters means 10 characters means that is 10 bytes. Yes or no? Okay, so 10 bytes. Now you tell me, in 1 second, this keyboard can transfer how much data? Let me know. This keyboard, how much data it can transfer in 1 second? That is 10 byte. Yes or no? So remember the speed of keyboard. Okay, the data transfer rate of this keyboard, that is per second. Per second it can transfer 10 bytes. Okay, and remember one thing. This will happen when you are very fast. The user. Okay, if you are typing and let's assume you are very fast, then it will happen. Yes or no? If you are slow, then it will not happen. For example, if you are slow and let's assume in 1 second you are typing only one key, then the speed of keyboard, that is only one key, or I can say 1 byte per second. Yes or no? But let's assume that you are very fast typing person. Then you can see the speed of keyboard, that is 10 bytes per second. This is the data transfer rate of keyboard, that is 10 bytes per second. So this keyboard, it can transfer, remember, it can transfer, it can provide 10 bytes per second. Okay, but remember, CPU and main memory, they are very fast. CPU can execute millions of instructions per second. Remember, this CPU, it can execute millions of instructions per second. Also it can transfer GB per second. Okay, megabytes, gigabytes per second. So remember, compare the speed of CPU, main memory with keyboard. CPU and main memory, they are very fast. What they can do, they can transfer megabytes per second. Okay, for example, let's assume this main memory, maybe this can transfer megabytes per second. Okay, per second. And this CPU, this can transfer maybe gigabytes per second. Okay, this can transfer maybe gigabytes per second. So can you see the difference in the speed? Okay, so very simple point, that IO devices are very slow. For example, here you have keyboard and the data transfer rate of keyboard, that is 10 bytes per second. So this keyboard can provide you 10 bytes per second. But you can see the speed of main memory and CPU, that is very fast. The data transfer rate of main memory, that is megabytes per second. Okay, and the data transfer rate of CPU, that is gigabytes per second. So these devices are very fast. But this keyboard cannot provide at this speed. Yes or no? This keyboard, this cannot provide data at this speed. Do you agree? Okay, so at this point, you can see if the keyboard is transferring data to main memory, then you can see that keyboard does not provide data at the speed at which CPU is operating. CPU and main memory, they are operating at very fast speed, but this keyboard cannot provide you data at that fast speed. Okay, so this is the idea. I hope you understood the challenges. Did you understand? Let me know. So you can see the input device may not be ready. Yes or no? Your input device that may not be ready to receive the data at the speed at which processor is providing the data. Okay, similarly, the output device may not be ready to receive the data at the rate at which processor is providing the data. So very simple. Okay, is this point clear? Let me know. So this is the issue, remember, in the IO data transfer. I hope you understood. Now let's move on. Now what we need to do? Now we need to study three data transfer techniques. One is programmed IO, another is interrupt driven IO, and another is data direct memory access, DMA. Okay, in this lecture, let's study these two. So let's start with the first one. We will also see what is the difference between these two and which of them is better. Okay, we will see which of them is better. Is this technique better? Is this technique better? So we will do their comparison. Also, we will see what are these techniques for IO data transfer. Okay, again, I'm telling you, when you say IO data transfer, then data transfer is happening between main memory and IO via CPU. Yes or no? Between main memory and IO via CPU. So very simple. Now let's see the first one, that is programmed IO. The another name for this, that is program controlled IO. Okay, program controlled data transfer. Another name is polled IO. So these are different names for this technique. Okay, in this technique, what we do? First of all, let me tell you that in this technique, what we are going to do, we are going to transfer data between IO device and main memory via CPU. Okay, via CPU, the data will go. Okay, is this clear? So, very simple point. In this programmed IO, this is going to happen that data will go via CPU. Okay, so let me write it here that this is what you want to do. You want to do data transfer between IO and main memory, but the data will go via CPU. Okay, is this clear? So let's assume there is CPU here. So this is our CPU. Now this data transfer we want to do. Okay, but this data will go via CPU. So like this, you can understand like this. Is this clear? So if I want to transfer data from main memory, from IO device to main memory, if I want to do this data transfer, then what will happen? First, the data will be loaded in CPU register, then CPU will store in main memory. Okay, similarly, if you want to do data transfer from main memory to IO, then what will happen? First, the data will be loaded in the CPU register. Okay, then the CPU will transfer the data in IO. Okay, so this is what will happen. So you can see there is complete involvement of CPU. Yes or no? Okay, the data is going via CPU here. So very simple, the involvement of CPU is there. Okay, now let's see this. So let's see the definition of programmed IO. So you can see CPU executes a program that will transfer data between IO device and main memory. That is the reason this is called programmed IO. Why this is called programmed IO? Because CPU is executing a program and this program will have full control on the data transfer between IO device and main memory. Okay, don't worry, you will understand this. Right now you might be thinking, sir, I did not understand, but don't worry. So you will understand this. Okay, so first let me tell you a very quick analogy of this program controlled IO. The name itself is telling you program controlled IO. So let me tell you one quick analogy. Okay, see, you want to do data transfer. Let's assume you want between main memory and IO device. Yes or no? So let me give you analogy of this program controlled IO. The analogy is like this. Let's assume I tell you to do some task. I give you some task and I ask you that do this task. Okay. Now, after giving this task to you, I'm continuously asking you, have you completed? Have you completed? Have you completed? Are you finished? Are you finished? Are you finished? Yes or no? Okay. So remember, after giving you the task, I am not doing any useful task. Okay, what I'm doing after giving you the task, I'm asking you continuously I'm asking, are you, did you complete it? Did you complete it? Are you finished? Are you finished? Yes or no? Is this clear? Now maybe you will take 10 minutes. Let's assume you are taking 10 minutes to complete the task. Then for the 10 minutes continuously I'm asking you, are you finished? Are you finished? Are you finished? Yes or no? Is this clear? So this is the quick analogy of program controlled IO. Let me know. So remember, I'm continuously asking you, are you finished? Are you finished? I'm not doing any useful work. I am not doing some other useful work. Yes or no? I am continuously asking you, are you finished? Are you finished? This is called polling. Basically, I am continuously polling. Okay, I am continuously checking, are you finished? Are you finished? So this is called polling. That is the reason this is called polled IO. Is this clear? So you can see that is the reason this programmed IO technique, this is also called polled IO, because I'm continuously asking you, I'm continuously polling, are you finished? Are you finished? Are you finished? Okay, is this clear? So this is just a quick analogy. Okay, now let me give you another analogy. So let me give you one detailed analogy. In this detailed analogy, basically we will understand the concept and all the important points in this detailed analogy. So let me explain. Let's take the example of bank. Okay, in this analogy, bank analogy, I'm giving you bank analogy. Let's assume that I am the CPU. Okay, is this clear? So let's assume this is me. This is me. I am the CPU. I am the CPU. Okay, and or you can say I'm the bank manager, or I can say I'm the basically manager, or I can say boss. Okay, is this clear? So very simple that I'm the CPU, or you can consider CPU as the boss. Now what I'm doing, I'm executing a program, I'm doing some task. Yes or no? I'm doing some task. So this is my task I'm doing. Okay, like this, like this, like this, like this, I'm doing some task. So this is the task that I'm doing. Okay, I'm doing some work, let's assume. Okay, so when I'm doing some work, then what it means, CPU is doing some work. What that means? That means CPU is executing some program. Yes or no? Okay, CPU is executing program. Agree? Correct? CPU is doing some work. That simply means CPU is executing some program. So let's assume I'm doing some task. Okay, I'm executing this program like this, I'm executing. Okay, now let's assume this is you. Okay, this is you, and let's assume that you are the employee. Okay, you are the employee in the bank, and this employee basically, okay, and let's assume this is the IO device. IO device is the ATM. Okay, this ATM machine, this is the IO device. Okay, this ATM machine, let's assume this is your IO device. Now understand this. So you are the employee. Let's assume this is you. Okay, this is you. You are the employee in the bank, and this is ATM machine, which is the IO device. Now notice one thing, that IO device will not directly communicate with the boss. Yes or no? The manager will not directly communicate with the ATM machine, because this is the manager. So what it will do? Okay, there is an interface. So you are the interface. Let's assume. Okay, this is you. You are the interface. Okay, you are the interface. Correct? So remember, you are the interface. Is this clear? You are the interface. So very simple, like this. You are the interface between ATM machine and bank manager. Okay, you are the interface. Now, now see what will happen. Now let's assume that when I'm executing this program, I'm the CPU, I'm the boss. Okay, now let's assume I'm executing this program, I'm doing some work. Okay, now there is an instruction. Let's assume there is an instruction I10. Okay, let's assume this instruction. What is this instruction I10? This instruction says that basically collect 3 lakh rupees from ATM and deposit in the, let's assume, deposit in the bank locker. Okay, that bank locker, what is that? That is your main memory. Is this clear? Bank locker, that is your main memory. So remember, this is your main memory. This is our main memory. Okay, you can consider this main memory as the bank locker. Okay, is this clear? As the bank locker. So very simple. Now this is our main memory. Now what is our task? Let's assume that this instruction, this I10 instruction, what is that? Okay, when I'm doing some work, then this I10 instruction, this is that collect 3 lakh rupees, basically transfer 3 lakh rupees from ATM to bank locker. Is this clear? So what is this instruction I10? Let me tell you, this instruction I10, this is a transfer, this is transfer 10 lakhs rupees, okay, from ATM, which is the IO device, right? Yes or no? Which is the IO device, from ATM to bank locker. To bank locker. So did you understand? So this here, remember this ATM, what is this? This is your IO device, correct? This is the IO device. So we want to do data transfer from IO device to main memory. This bank locker, this is your main memory, let's assume. Okay. So this is what we want to do. Is this clear? So the instruction is transfer 3 lakh rupees from ATM to bank locker. Now, let's assume that ATM, will it give you 3 lakh rupees in one go? Will it give you 3 lakh rupees in a single, I can say in single time? Okay, no. Okay, it will give you, let's assume it will give you 1 lakh rupees. You know, ATM has the limit, right? Okay, it can give you maximum 1 lakh rupees, it can give you at one time. Let's assume. Okay, so let's assume that ATM is giving you this ATM. Okay, this IO device, this ATM. What is the data transfer rate of this ATM? The data transfer rate of this ATM, that is, it can give you 1 lakh rupees. It can give you 1 lakh rupees. Okay, and let's assume for that 1 lakh rupees, let's assume it is taking per minute. Okay, it can give you 1 lakh rupees per minute. Correct? Yes or no? This is reasonable assumption. Do you agree with me? When you go to the ATM and let's assume you are taking some money, then I can assume 1 minute it will take. Yes or no? Agree? So let's assume in the single transaction, this ATM machine, this will give you 1 lakh rupees. So this is the data transfer rate of ATM machine, that is 1 lakh rupees per minute it can give you. But how much rupee we want? We want to transfer 3 lakh rupees from ATM to main memory. Yes or no? So what I will do, when this instruction I10 comes, I am doing my work. I'm executing the instructions because I am the CPU. I am executing the instructions. Now this I10 instruction comes. This I10 instruction tells me that do this data transfer. Yes or no? From the ATM to bank locker, do this data transfer. So what I will do, tell me what I'm going to do. Will I go to the ATM machine to take the money? Will this manager go to the ATM machine? No, this manager will not go. Yes or no? This manager will tell the employee. So very simple, this manager will give the command to the employee. Okay, is this clear? So remember, what the first step in this complete situation, what is the first step? The first step is that I'm executing my task, I'm doing some task, and I encounter this instruction. Yes or no? This data transfer instruction I encounter. So let's call it task, let's call it step number 1. Okay, let's call it step number 1. What is the step number 1? Remember, I'm doing my work. I'm the CPU. I'm executing instructions. Okay, like this, I'm doing some work, and then suddenly this I10 instruction. This is the instruction for data transfer. I want. Okay, so I encounter this data transfer instruction. Okay, this data transfer instruction. This I10 I encounter. Okay, now when I encounter this instruction, then I need to execute it. Do you agree? Okay, I need to execute this I10 instruction. So to execute this I10 instruction, what I will do? I will give the command to the interface. Yes or no? Okay, so the second step, what is the second step? Second step, I will give command to the interface. Yes or no? CPU gives a command. Okay, CPU gives command to interface. Do you agree? Please tell me. See, step by step, I'm telling you what will happen. And you can agree that these things will happen. Okay, because the manager will not go to the ATM machine. The manager will tell the employee. Yes or no? So very simple. When the manager will encounter this data transfer instruction, this I10 is data transfer instruction. Okay, this I10, what is this? This is data transfer instruction. So when the CPU will come across this data transfer instruction, then the CPU will give command to the interface. Okay. Okay, and what will be the command? Tell me. The command will be that I want 3 lakh rupees from the ATM machine to the bank locker. Yes or no? This is the command. So the CPU will give command to the interface. Now what this interface will do? It will it will it will basically collect money from the IO device. Yes or no? So remember this employee, or I can say this interface, what it will do? It will start collecting rupees from the ATM machine. Yes or no? Agree with me? So very simple. What this employee will do? Let's assume this employee has a bag. Okay, this employee has a bag, right? Okay, to put this money. Okay, to put this money. So this employee has a bag. Okay, in this analogy, what is the bag? Can you tell me? In this interface, you have a bag. Basically, this employee has a bag to collect the money. Okay, to collect the data. This IO device is giving you the data. So to collect the data, okay, to collect the data, this employee has a bag. So in this analogy, what is this bag? This bag is your buffer. Yes or no? That is your data register. So very simple. So remember this bag is your buffer. Okay, so in this analogy, this bag is the buffer. Okay, this is your data register. This is your data register in the interface. Okay, or you can call it buffer. Correct? Okay, so very simple. So this bag is your data register, or I can say buffer. Now what will happen? So let's assume the capacity is 1 lakh rupees, because you can see the ATM machine will give you 1 lakh rupees per minute. Let's assume the bag capacity is 1 lakh rupees. Okay, let's assume the bag capacity. Let's assume the bag capacity means the buffer capacity. What is that? The data register capacity. What is that? That is, let's assume 1 lakh rupees. Okay, let's assume. So you can easily see that what this what this employee will do, what this interface will do, it will collect data from the IO device. So this IO device will give the data to the interface. Okay, now let's assume, now you can see now what will happen. See the third step. Okay, the third step is, you can see the third step is, this is the third step, that IO device will collect data from here. Okay, yes or no? This is the third step. Third step is that IO device, this interface, sorry, this interface, or I can say you will collect data from the from the IO device. So very simple. Okay, this is the third step, that you will collect data from IO device. Okay, from IO device. Now meanwhile, tell me, okay, now let's assume that it will take 5 minutes, okay, or maybe 1 minute, right? Okay, so let's assume I told you that it will take 1 minute. This ATM machine, it will give you, it will take 1 minute to give you 1 lakh rupees. Agree? Okay, to give you 1 lakh rupees, it will take 1 minute. Now notice one thing. In this 1 minute, what will happen? In this 1 minute, in this program controlled technique, or I can say in this programmed IO, during this 1 minute, what will happen? This interface is collecting data from the ATM machine. Okay, this interface is collecting data from the IO device, but the CPU, what it will do? It will continuously asking. It will continuously ask, okay, have you collected 1 lakh rupees? Have you collected 1 lakh rupees? Have you collected 1 lakh rupees? So you can see this ATM machine will give you 1 lakh rupees per minute. So this ATM machine, this IO device will take 1 minute to give you the data. Okay, but this CPU will continuously ask, okay, have you collected 1 lakh rupees? Have you collected 1 lakh rupees? Like this, it will continuously ask, have you collected, have you collected, have you collected? Okay, now notice one thing, that what this what this employee will do, there is a status register also. Okay, so let's assume this employee is keeping a status also. So this is the status, whether I have collected the data or not. Yes or no? This IO device, whether this has given me the data or not. So there is a status register. Okay, in this status register, you can see this employee will write not ready. Okay, means the data is not ready right now. Okay, so let's assume this zero means not ready. Okay, so let's assume this status. Okay, there is a status register. There is a status register. In this status register, this bit, let's call it status bit or flag. Okay, let's call it status ready bit or flag. Basically, let's call it ready or not. Okay, this is your, I can say, ready bit, or you can call it flag bit. Okay, flag bit. So you can easily see that this bit, if this is zero, then what will happen? If this ready bit, if this is zero, then means data not ready. Data or device that is not ready. Yes or no? Or I can say data not collected. So data not ready. Okay. And if this is one, then it simply means data ready. Okay, is this clear? So very simple. What the CPU will do, let me tell you. In this 1 minute, because the ATM machine, this IO device will take 1 minute to give you 1 lakh rupees. Now during this 1 minute, okay, during these 60 seconds, what the CPU will do? The CPU will continuously check this status register. This CPU will continuously check this status register. Okay, continuously check. Is this zero? Is this zero? Is this zero? Is this zero? Okay, is this clear? So the CPU will continuously check this status register. Is this zero? Is this zero? Is this zero? Then you can see after 1 minute, what will happen? Tell me. After 1 minute, what will happen? This will become one. Yes or no? After 1 minute, the 1 lakh rupees will come here. Okay, the data will come in the data register. So you can see after 1 minute, this interface will collect the data. So 1 lakh rupees will come in the bag, in the buffer. And what this interface will do? This interface, okay, you are the employee, you will make this status bit 1. Okay, 1 means the data is ready now. Okay, now remember, will you go to inform this CPU? You are the employee. Will you go to the boss and will you inform that data is collected? Let me know. Will you go to the boss and will you inform that data is collected? No, 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 no. Remember, this CPU is continuously checking your status register. Okay, remember, this CPU is continuously checking. This CPU is continuously checking this status register. So when the CPU will see, okay, remember, when the CPU will see that this status bit is 1, now the CPU knows that, okay, data is ready. Now what this CPU will do? Now this manager, what this manager will do? Now this manager will take this 1 lakh rupees, okay, and it will take this 1 lakh rupees. So this 1 lakh rupees, where it will go? It will go to CPU register first. Okay, first it will go to CPU register. Here you have CPU register. So first this 1 lakh rupees, this will go to CPU register. Okay, CPU register. First it will go to CPU register. Then from that CPU register, it will go to the main memory. Okay, is this clear? Who will do this? The CPU will do. Is this clear? So CPU will take this 1 lakh rupees, it will store in the CPU register, and then this money will go to the main memory. From the CPU register, this 1 lakh rupees, this will go to the main memory. Okay, is this clear? Now, interesting thing, there are two things you should notice. What is that? The first one, that remember, the employee will not inform the CPU. Okay, this interface or the employee, this employee is not going to inform the CPU. What will happen? The CPU will continuously check the status bit. Okay, the CPU is continuously checking, are you ready, are you ready? Okay, yes or no, is this status bit, this CPU will continuously check. Okay, so this is the first thing, that interface will not tell the CPU, interface will not inform the CPU that data is ready. What will happen? The CPU is continuously checking. This is called polling. Okay, the CPU is continuously polling, is the data ready, is the data ready? Okay, that is the one thing. So that is the reason this is called polled IO. Yes or no? Because the CPU is continuously polling, this CPU is continuously checking the status. Okay, is the data ready, is the data ready, is the data ready? So this is called polling. So this is the one thing that you should understand. The second thing to understand, that is the second thing, that is, remember, everything is executed by the CPU. Yes or no? The CPU is in the complete control here. Do you agree with me? The CPU is in complete control here, because remember what is happening. The CPU was doing some task, the CPU was executing a program. Remember, the CPU, the bank manager, is executing some program, and in this program, this CPU is encountering this data transfer instruction. So remember, this data transfer instruction, this is inside this program which is CPU executing. Yes or no? This is data transfer instruction, this is inside the program that is executed by the CPU. That is the reason this is called programmed controlled IO. Because in this program which is executed by the CPU, in this program we have this data transfer instruction. Okay, so that is the reason this is called program controlled IO. Also remember, the CPU is in complete control, and the CPU is not doing any useful work when this data is being collected. Yes or no? When the interface is collecting the data from the IO device, this interface, when this is collecting data from the ATM machine, from the IO device, then CPU is not doing any useful work. CPU is not doing some other work, some other useful work. What CPU is doing? CPU is waiting and also checking. Okay, is the data ready, is the data ready? Once the data will be ready, then remember, the employee will not tell the CPU. No, the employee will not tell the CPU. What will happen? The CPU will check the status bit. Okay, CPU is continuously checking the status bit. So what this interface will do, what this employee will do, this employee will make this bit 1. This interface is going to make this bit 1. Now this bit 1, this simply means that data is ready. Now the CPU is continuously checking, and when the CPU sees that, okay, this bit is 1, it simply means data is ready. Now this CPU will take this data to the CPU register, and from there it will go to the main memory. Okay, so this is the complete programmed IO analogy. Now, one more thing. So far, how much money we transferred? Let me know. So far, how much money, how much data did we transfer? We transferred only 1 lakh rupees. But how much we need to transfer? Tell me, how much we need to transfer? We need to transfer 3 lakh rupees. Now what will happen? Tell me. So after transferring 1 lakh rupees, after transferring 1 lakh rupees, now what will happen? Now again the same thing will happen. Okay, again the same thing will happen. Again the CPU will continuously check. Remember, when you transfer this 1 lakh rupees, now the 1 lakh rupees has gone to the main memory. Now this interface, okay, this interface will make this bit 0. Yes or no? So this bit will become 0. Is this clear? Now again 1 lakh rupees this interface is collecting. You are the employee, you are collecting 1 lakh rupees. Is this clear? Again the same thing will happen. Now what will happen? Again the CPU is continuously checking, is the data ready, is the data ready, is the data ready? Okay, and remember, in 1 minute, because this ATM machine will take 1 minute, so after 1 minute what will happen? This data will be ready, another 1 lakh rupees will be ready. Okay, now what this interface will do? When 1 lakh rupees is ready, then the interface will make it 1. Now the CPU is continuously checking, is this one, is the status 1? Means the data is ready. When the CPU will see that data is ready, now what will happen? When the CPU will see that data is ready, now what will happen? The same thing, CPU will take this data, it will store in the CPU register, and then it will store in the main memory. Is this clear? Now tell me, another 1 lakh rupees came, another 1 lakh rupees came. Now tell me what will happen? Is our task over? Is our task over? No, our task is not over. Now again the same thing will happen. What will happen? See, again this bit will become 0. Okay, because Now the data is not ready. Again, this bit will become 0. Again, what will happen? This interface will collect 1 lakh rupees from the ATM machine. The ATM machine will take 1 minute. Okay. In 1 minute, 1 lakh rupees will come to this interface. Now, when the interface will get 1 lakh rupees, during that time, during this 1 minute, remember, during this time, the CPU is continuously checking, is the data ready? Is the data ready? The CPU is continuously checking. Okay. But the data is not ready. So the CPU is continuously checking. Now, when the data will be ready, after 1 minute, what will happen? The data will be ready. So this interface, this employee, this interface will make this bit 1. Now the CPU is checking, okay, is the data ready? Now, when the CPU will see that this bit is 1, now what will happen? Now the data is ready. The CPU knows that, okay, data is ready. Now what will happen? Again, the CPU will take this 1 lakh rupees. It will send this 1 lakh rupees to the CPU register. From the CPU register, the data will go to the main memory. Okay, so another 1 lakh rupees will come. Now the task is over or not? Tell me. Now the task is over, yes or no? So when the task is over, now what will happen? Now the CPU, means this boss, this bank manager, it will execute I11, I12, I13. Is this clear? Please tell me. So this is your programmed controlled IO. So this complete analogy, did you understand? Let me know. This is the complete concept. Let me tell you, this is what actually happens. Everything I told you. So did you understand what happens in the programmed controlled IO? Why this is called program controlled IO? Can anyone tell me? What is the reason this is called program controlled IO? Why this is called program controlled IO? Tell me. What is the reason this is called programmed IO or program controlled IO? This is called programmed controlled IO because CPU is executing a program. Remember, the CPU, this is executing a program. Okay, CPU is executing a program. This program, the CPU is executing. So remember, this CPU, this is executing a program, and in this program, this instruction comes, which is data transfer instruction. Okay, yes or no? After some time, maybe again another instruction will come, maybe I22, that is also data transfer instruction. Okay, so remember, these are data transfer instruction. Let's assume this I10 and I22. This I10 and I22, let's assume these are data transfer instructions. These are data transfer instructions. Okay, so remember why this is called program controlled IO. The name itself is telling you program controlled IO. Okay, program controlled data transfer means the CPU is executing some program. CPU is doing some work. CPU is executing some program. During this program, this instruction comes. This instruction is data transfer instruction. So to execute this instruction, what the CPU will do? To execute this instruction, this CPU, what it will do? It will give the command to the interface. Yes or no? It will give command to the interface. After giving command to the interface, what this interface will do? The interface will collect data, yes or no, from the IO device. The interface is going to collect data from the IO device. Remember, very simple point. The CPU is doing some work. The CPU is executing a program, and this CPU is encountering this instruction, which is data transfer instruction. So when the CPU will see this data transfer instruction, what the CPU will do? To execute this instruction, because we need to execute this instruction. To execute this instruction, what the CPU will do? CPU will give command to the interface. Okay, will give command to the interface. So the command will go to the interface. Now what this interface will do? This interface will collect data from the IO device. Okay, from the IO device, this interface will collect data. Okay, there is data register here. There is buffer. Okay, there is buffer, and there is status register, and there is a status register. Yes or no? Correct. Now what will happen? So remember, after this CPU will give command to the interface will collect data from the IO device, but IO device is very slow. Do you agree? IO device is very slow. So this data collection will take some time. During this time, what will happen? When this interface is collecting data, then let's assume 1 minute. Let's assume this IO device is taking 1 minute. Okay, let's assume it is taking 1 minute. Now remember, during this 1 minute, what will happen? The CPU is continuously checking this status register. Okay, CPU's eyes. Okay, CPU's eyes, they are on the status register. So CPU is continuously checking this status register. Is the data ready? Is the data ready? Okay, when the data is not ready, then this status bit will be 0. Status bit is 0 means the CPU is continuously checking this bit. If this bit is 0 means data is not ready. CPU is continuously checking, remember, checking. Then when the data will be ready, after 1 minute, the data will be ready, then the interface will make this 1. This bit will become 1. Now remember, the interface will not inform the CPU. Please understand, this interface, this is not going to inform the CPU. Okay, what will happen? The CPU is continuously checking the status bit. So the CPU will check this status bit and it will see that this bit is 1. What it means? It means the data is ready. Now when the data is ready, then what will happen? The CPU will take this data to the register, and from that register the data will go to the main memory. Okay, is this clear? So you can see the CPU register. This is the register, and then finally it will go to the main memory. Okay, so very simple. This is the complete thing. Is this clear? Let me know. So very simple. I hope you understood. This is the complete idea. And why this is called polled IO? What are the reason this is called polled IO? Tell me. What are the reason this is called polled IO? Because CPU is continuously checking the status. Yes or no? This CPU, this is not doing some useful work. Okay, see, this IO device will take 1 minute to give you the data. Okay, so this interface is collecting data from the IO device, but this IO device will take, let's assume, 1 minute. In this 1 minute, during this 1 minute, CPU is not executing some other program. CPU is not doing any useful work. CPU is continuously polling. Is the data ready? Is the data ready? Is the data ready? CPU is continuously checking this status register. So that is the reason this is called polled IO. Okay, is this clear? That is the reason this is called polled IO, or I can say that is the reason this is called polling. Okay, is this clear? Very simple. So this is the complete idea. I hope you understood. So you can see this is your register, this is your interface, right? Okay, I already told you that IO device that is not connected to CPU directly. Okay, there is an interface between. So this is your interface. You can see this is your interface. In the interface, we have data register, or you can call it buffer, and there is status register. In the status register, this is your flag bit. Okay, this is your flag bit, or I can say this basically indicates data is ready or not. This indicates data is ready or not. Data is ready or not in the interface, in the in the interface data register, in the interface data register, interface buffer. Okay, in the interface buffer, because this data register, this is also called buffer. So very simple. So this is the idea. So remember, in this interface there is a status register. In this status register, this is the flag bit. If this bit is 0, means data is not ready. If this bit is 1, means data is ready. Is this clear? So you can see when this flag bit, okay, this flag bit, when this is 0, means data not ready. Data not yet ready. Okay, yes or no? And when this bit is 1, then it means data is ready. Data is in our buffer. Data is in the buffer. Okay, data ready. Data is in the buffer. Ready means in the buffer. Okay, when we say ready, that simply means in the buffer. Data in buffer. Okay, is this clear? So very simple point. Now you can see this is the complete thing that will happen. Here you can easily notice what will happen. Tell me. So what are the initial thing? See, okay, see, you can see the CPU will read the status register. Yes or no? The CPU is going to read the status register. Okay, so in this status register, the CPU will check the flag bit. If this bit is 0, if this bit is 0, then again the CPU will check. Yes or no? See, if this bit is 0, the flag bit, you are checking the flag bit. If this bit is 0, then what the CPU will do? CPU will continuously check. This is called polling. Yes or no? This thing is called polling. Do you agree? This thing is called polling. That CPU is continuously checking. CPU is continuously checking. This is called polling. Now, when this when this flag bit will be 1, when this is 1, then what will happen? Then very simple. Now you will read the data register. Okay, read the data register means what? Now the data will go from the buffer to where? Buffer to CPU. Yes or no? The data will go from buffer to CPU. Okay, now then what you will do? Then the data will go from CPU to main memory. Okay, and then you will check, is the operation complete? Is the operation complete? If the operation is not complete, then the same task will repeat. Yes or no? If the operation is not complete, then again you will check the status register. You will check the flag bit. If the flag bit is 0, then you will continuously check. If the flag bit is 1, then what you will do? Then data will go from buffer to CPU. Then the data will go from CPU to main memory. If the operation is complete, then you will continue with the program. Yes or no? I told you that CPU is executing a program, correct? I told you CPU is executing a program. Okay, this CPU is executing this program. CPU is executing. Okay, so you can see when this I10, this is your data transfer instruction. When this will be over, means when the operation will be over, then you will continue I11, I12, I13 like this. Okay, is this clear? So this is the program which CPU is executing. So that is the reason this is called program controlled IO, because in this program, the data transfer instruction is there, and because of this data transfer instruction, the CPU is doing this complete thing. Okay, is this clear? So very simple, programmed IO. You can see, are you ready? Are you ready? Okay, because in this programmed IO, what we do, what the CPU will do, CPU will do the polling. Means the CPU will continuously ask, are you ready? Are you ready? CPU will not do any useful work. CPU has nothing to do, no useful work CPU will do. Okay, during this time. Now let me give you one more example. Okay, so that you can clearly understand what is this programmed IO, and you can also understand why this is called program controlled IO. Why this is not IO controlled? See, this is program controlled. This is not IO controlled. Okay, I will explain. Don't worry. So let's take the example of ATM machine. You have already used the ATM machine, right? In the ATM machine, what is the first task you do? Can anyone tell me what is the first task? This is the first task. Yes or no? You will insert the ATM card in the ATM machine. Okay. Then the second task, what it will be? Then you will press some buttons. Okay. You will put your ATM pin. Okay. You will put the how much money you want. Okay. So basically, this is the ATM machine. Now let's take the ATM machine example. In this example, try to understand. In this example, ATM machine is your CPU. Okay. Is this clear? So who is the CPU? The ATM machine. The ATM machine is the CPU. Remember here, the ATM machine. This is your CPU. In this example, okay, I am taking a new example. Remember, I am taking a new example. Consider the ATM machine. You are taking, let's assume you want money from the ATM machine. Now, this ATM machine, this is your CPU. Okay, is this clear? Now, notice one thing. Tell me what the first step in the ATM machine. What the first step? Remember, ATM machine has some program. Do you agree? ATM machine is executing a program. There is a program that ATM machine is executing. Do you agree? Do you agree that ATM machine is executing a program? Okay, and remember the program, the first instruction, what that will be? What do you think? What the first instruction? In this ATM machine, remember, in this ATM machine, there is a program, right? Okay, so this ATM machine is executing a program, correct? Now, in this program, what the first instruction? Can anyone tell me? What is the first instruction? The first instruction is like this. The first instruction is this ATM machine, this CPU is continuously checking the status of, see, this, okay, what this is called, where we insert the ATM, what this is called, let me know. What this is called? Okay, tell me where we insert the ATM. So let's assume this is a, okay, ATM entry point. Okay, so maybe you can call it where we insert the ATM. What this is called? Anyone can tell me? So let's assume this is your ATM slot. Okay, ATM slot. Yes, yes. Okay, so you can call it ATM slot, right? Yes or no? This is the ATM slot. Now, so what the first thing? Okay, what this ATM machine is doing? This ATM machine is continuously checking the status of ATM slot. Yes or no? This is continuously polling, or I can say this is continuously checking. This is continuously checking status of ATM slot. Agree? This is the first step or not? Okay, in the ATM machine, this is the first step, that this is continuously checking. This is continuously checking. Remember, this is the program which is executed by the ATM machine. Okay, so you can see the ATM machine is executing this program. So very simple. Okay, so in this program, remember, very simple thing, that ATM machine is continuously checking. Okay, this ATM slot. Okay, there is a ATM slot in the ATM machine. This is your ATM machine. In the ATM machine, this is the ATM slot. You can ATM slot. Okay, you can call it IO. You can call it port, or okay, you can call it port. Anyway, this is your ATM slot. Now, remember what will happen. Now, let's assume you did not come. Okay, let's assume there is no one in this ATM room. Okay, in this room, there is no one. Then what this ATM machine will do? It will continuously check this. Okay, and there is keyboard also. There is keyboard also. Okay, there is keyboard also. So this is keyboard in the ATM machine. This is the keyboard. Now, notice what will happen. See, initially, when you do not insert the ATM in the ATM slot, in this ATM slot, if you do not insert the ATM, and let's assume you are pressing the buttons. Okay, you go to the ATM, ATM machine, and let's assume you do not insert the ATM. Let's assume, okay, you are not inserting the ATM, you are directly pressing the ATM button. Now what will happen? If you press the keyboard button, what will happen? Tell me. Nothing will happen. Yes or no? If you press the keyboard button, nothing will happen. So what it means, just understand this, very important. What it means, if you press the keyboard, nothing is happening. Why? Because the CPU is not polling the keyboard. Yes or no? CPU is not polling the keyboard. CPU is not checking the keyboard. CPU is checking only the ATM slot. Why CPU is checking the ATM slot? CPU is continuously checking the ATM slot. Okay, did the ATM come? Did someone insert the ATM? Did someone insert the ATM? Yes or no? Did someone insert the ATM? So you can see ATM machine, this CPU is continuously checking this ATM slot. Why this is checking this ATM slot? Because it is written in the program. Okay, because it is written in the program. Do you agree with me? This is very important point. Why I am calling it program controlled IO? Program controlled IO. Understand this, program controlled IO. Okay, remember this, because remember, if you press the keyboard button without inserting the ATM, if you do not insert the ATM, if you directly press the keyboard button, nothing will happen, because the first instruction is, this is the first instruction, that is, you are continuously checking the ATM slot. Yes or no? So in this program which is run by the CPU, okay, right now the CPU is not checking. In this program right now we are not checking the keyboard. Yes or no? Because we are not checking the keyboard, so if you press the keyboard button, nothing will happen. Okay, so from here what I want to tell you, I want to tell you that in this program controlled IO, in this program controlled IO, can the IO device give signal for attention? Is it possible? In this program controlled IO, can the IO device, can the keyboard, can the IO device give signal for attention? Please tell me. Can this keyboard give signal for attention to the ATM machine, to the CPU? No, it will not give. So that is the reason this is called program controlled IO, because the CPU is executing a program. This program the CPU is executing, and you can see when the first instruction is you are continuously checking the status of the ATM slot. Okay, at this time when you are checking the status of the ATM slot, at this point of time, if someone press the keyboard, then nothing happens. Okay, means the keyboard cannot give signal to the CPU. The keyboard cannot give signal to the CPU for attention. Okay, is this clear? Everything is controlled by the CPU. Remember, everything is controlled by the CPU, everything is controlled by the program. Okay, so very simple. So now what will happen? Now remember, the CPU is continuously checking, is the ATM inserted, is the ATM inserted. Now when you insert the ATM, now what will happen? Initially, let's assume this ATM slot, okay, let's assume the status bit is 0. This ATM slot, okay, here also the status bit is there. Here also there is status register, register. Okay, and this is your flag bit or status bit. You can call it flag bit or you can call it status bit. So initially the status bit is 0. What it means? The CPU is continuously checking this. That initially this status bit is 0 means no one has inserted the ATM. Now let's assume after 10 minutes. After 10 minutes you insert the ATM. Okay, you insert the ATM after 10 minutes. So this will become 1. Now the CPU is continuously checking. Yes or no? The CPU is continuously checking. So when the CPU will see that, okay, this is 1, what it means? It means someone has inserted the ATM. Now what will happen? After that, what will happen? What is I2 now? What is I2? Now the I2 is now press your ATM pin. Insert the ATM pin. Yes or no? Now press ATM pin. Okay, yes or no? Agree? So now this is the thing. Now what will happen? Now the CPU, now CPU will give attention to the keyboard. Is this clear? Because the next instruction is insert ATM pin. So what will happen when you see this instruction? When the CPU will see this instruction, what the CPU will do? CPU will give command to the keyboard. Now the command will go to the keyboard. Who is giving the command? The CPU is giving. The CPU is giving command to the keyboard. Okay, and again what will happen? Okay, again what will happen? The CPU is waiting. Yes or no? This keyboard interface. This keyboard interface. In this keyboard interface also there is status register and there is data register. Okay, how much data register we need? What is the size of data register we need? 4 bits. Can I say? Okay, can I say 4 bits? Maybe. Okay, so because ATM pin has, let's assume 4 digit, let's assume 1 digit is 1 bit, let's assume, okay, for just understanding purpose, let's assume this is the buffer, this is the buffer, okay, and there is status register also, this is status register. Now notice, so the CPU is executing this I2 instruction. I2 instruction is press ATM pin, okay, this is the I2 instruction. So when this CPU is executing this instruction, what the CPU will do, CPU will give command to the keyboard, okay, the command will go to the keyboard. Now what the keyboard interface will do, the keyboard interface is asking the user, okay, the keyboard interface is asking the user, this is the user. So the keyboard interface is asking the user that that basically press the ATM pin, yes or no. Now let's assume the user is taking, let's assume 20 seconds, okay, let's assume user is taking 20 seconds to insert the pin, okay, to type pin. Let's assume the user is taking 20 seconds to type pin. Is this clear? During this 20 seconds, what the CPU will do, will the CPU do some useful work, some other useful work? No, the CPU is continuously checking this status bit, okay, in the keyboard interface the CPU is continuously checking this status bit, the CPU is continuously checking, okay, did the user insert ATM pin, okay, so this CPU is continuously checking. Now when this bit will become 1, what it means, it means the ATM pin has been inserted. Now what the CPU will do, now CPU will do the instruction I3, that is verify pin, verify ATM pin, yes or no, and so on and so on. So that's it. So this is the complete idea. I hope you understood. Remember what I want to tell you, in this program controlled IO, everything is controlled by the program which is executed by the CPU. Okay, is this clear? So the IO cannot give any signal for attention. Let me know, did you understand? The IO device cannot give any signal for the attention. Everything is controlled by the CPU. The CPU is executing a program and everything is controlled by this program. In this program, if you want some data from keyboard, then there is an instruction. If you want some data from mouse, there is an instruction. If you want some data from hard disk, there is an instruction. So remember, CPU is executing this program and everything is controlled by this program. That is the one thing. That is one thing, that it is called program controlled IO, because everything is controlled by the program, everything is controlled by the CPU. The IO device cannot give signal for attention. Okay, for example, let's assume in this program, let's assume there is no instruction for printer. In this program, CPU is executing this program. In this program, let's assume there is no instruction for printer. Now tell me, can printer give signal to the CPU? If there is no instruction for the printer, then can printer give signal for attention? No. Yes or no? No, it will not happen. So very simple, remember that this is called program controlled IO. Did you understand this word, program controlled IO? Because everything is controlled by the program which is executed by the CPU. CPU is executing a program and that program is controlling everything. I hope you understood. So let's see this diagram. You can see what is the first step. The first step, you can see the CPU, what it will do, the CPU will give command to the interface, yes or no. You can see the CPU will give command to the interface. So CPU is giving the command to the interface. Now after that, what will happen, when this command goes to the interface, then the interface will collect data from the IO device, yes or no. Now meanwhile, when the interface is collecting data from the IO device, during this time what the CPU will do, the CPU is continuously checking the status bit, yes or no. The CPU is checking the status register. So the CPU will read the status of the IO module. Okay, if it is not ready, if the data is not ready, then this polling will continue. Okay, yes or no? This is called polling. This thing is called polling. So if the data is not ready, then CPU will continuously check. It is continuously checking. Are you ready? Are you ready? Is the data ready? Is the data ready? Now, if the data is ready, then what the CPU will do? Very simple. From the module, from the interface register, the data will go to the CPU, and from there, from CPU, it will go to the main memory. Yes or no? CPU will read from the IO module. Remember, CPU will read from the IO module, means from IO module, the data will go to the CPU. Then the CPU will write in the main memory. If the task is not done, now you will check, is the task done? If the task is not done, the same thing will happen. Again, what will happen? If the task is not done, then again the CPU will give read command to the IO module. The IO module will start collecting the data from the IO device. Okay, during this time, when this interface is collecting data from the IO device, during this time, CPU is continuously checking the status. CPU is not doing anything useful work. Okay, and you can see when the data will be ready, then again what will happen? The CPU will take data from the IO module, then CPU will store in the main memory. Okay, if the task is done, then CPU will go to the next instruction. So this is the complete thing about programmed IO. Okay, let me know, understood? So read this. What is the polling sequence? CPU will request for the IO operation. Who will request for the IO operation? IO device or CPU? Tell me. Who can request for the IO operation? In this programmed controlled IO, in this mechanism, in this technique, who can request for the IO operation? Who can request for the data transfer? CPU. Yes or no? I told you, because this is program controlled. This is CPU controlled. CPU is in the full control. So you can see CPU will request the IO operation. The IO module will perform the operation. The IO module, what it will do? The IO module will set the status bit. But remember, IO module will not inform the CPU. Read this. Read this line. IO module does not inform the CPU. What will happen? The CPU is checking the status bit. Okay, see, IO module will not inform the CPU, but CPU is checking the status bit periodically. This is called polling. CPU is checking status bit periodically. This is called polling. Okay, now, very simple. So this is the idea. So remember, IO module will not inform the CPU. IO module will not interrupt the CPU. Okay, when the data will be ready, then the IO module will set the status bit. IO module will make the status bit 1. Now the CPU is continuously checking, and when the CPU will see that status bit is 1, then CPU will do the data transfer. Okay, so this is called programmed IO because everything is controlled by the program. Let's read this. Whatever you understood, let's read this. So CPU is executing a program, I told you. So remember, CPU is executing a program that will transfer data between main memory and IO device. Data transfer is initiated by program, I told you. Yes or no? Who will initiate the data transfer? Data transfer is initiated by the program which is run by the CPU. So the CPU will initiate the data transfer. The processor is in total control of everything. The CPU is in total control of everything, and CPU will do all the work. Remember, CPU is going to do all the work. Remember, IO module does not inform the CPU. Okay, when the data will be ready in the IO module, when the data will be ready, IO module will not inform the CPU. What IO module will do? IO module will this is what IO module will do. It will just set the status bit. Okay, it will set the status bit. IO module will do this. Now after that, CPU will check the status bit periodically. Okay, periodically, again and again. Now what will happen? Read this. So the IO device itself, remember, the IO device does not have the capability to send signal for attention. I told you this, yes or no? In this program controlled IO, can the IO device send signal for attention? Is it possible? Is it possible that IO device can send signal for attention? Is it possible? No, that is not possible. IO device itself doesn't have the ability to send a signal for CPU attention. So remember, everything will be controlled by the CPU. Everything will be controlled by the program which is run by the CPU. Because CPU is executing a program. Everything is controlled by this program. Okay, and in this polling, remember, IO device cannot give signal for attention. But what CPU will do? CPU will periodically check whether you need attention or not. Okay, so understand the difference. IO device cannot send signal for attention. IO device cannot send signal for attention, but CPU will periodically check whether you need attention or not. Okay, whether the data is ready or not. CPU is continuously checking, is the data ready? Is the data ready? So this is the complete idea. I hope you understood. Now let's solve this question. This is GATE 2022 question. Let's focus on the statement number 3. Tell me what the answer. Focus on statement number 3. Is this statement true or not? The statement is saying, in polling, the CPU periodically checks. We are saying the CPU periodically checks the status bit to know if the device needs attention or not. So this is correct. Yes or no? This statement is correct because remember, the IO device cannot send signal to the CPU. I told you, in the programmed controlled IO, the IO device cannot send signal to the CPU for attention. But CPU will check periodically. CPU will check the status bit to know if the device needs attention or not. Okay, is this clear? So this statement number 3, this is true because CPU is periodically checking the status bit. Okay, to know if any device needs attention. Okay, so the CPU will check. The IO device is not going to inform. The IO device is not going to generate any signal, but the CPU will periodically check the status bit to check whether the device is ready or not. Okay, very simple. So in this question, which is true? Third statement is definitely true. So here option A, option B are gone. Okay, anyway, so third statement is definitely true. What I want to say, I want to say third statement, that is true. We have seen why this is true. Okay, let's move on now. So whatever we have seen that is written here, you can see when the processor is executing a program, I told you that in the programmed IO, what happens? The CPU is executing a program. Yes or no? So when the processor is executing a program and encounter an instruction which is IO instruction, when you encounter an instruction which is IO instruction, then what the CPU will do? Then very simple, the CPU will give command to the IO module. Now this IO module will collect the data from the IO device. Now the CPU is continuously checking the status register. Okay, is this clear? The CPU is continuously checking. Read this. The CPU regularly checks the status of the device by reading the status bit. Okay, is this clear? Very simple. So the CPU is continuously checking the status bit to check whether the data is ready or not. This diagram we have already seen. Okay, we have seen this. Is this clear? Let me know. Now, let's see this example. Don't worry about this code. You don't have to read this code. Okay, forget about this code. But what I want to tell you, I want to tell you that let's assume you want to transfer 100 words from memory to IO device. Okay, read this. What we want to do, we want to transfer 100 words from memory to IO device. Okay, from memory to IO device. From memory to IO device, we want to transfer, let's assume 100 words we want to transfer. Okay, and let's assume you are using program controlled IO. Okay, then it means what you will do, you will check the status by polling. Yes or no? You will continuously check the status. If the data is ready, then you will transfer. Okay, is this clear? Now remember, here what we want to do, we want to transfer 100 words. We want to transfer 100 words from memory to IO device. Correct? Okay, yes or no? Now remember, when one word will be ready, you will send it to IO. Then again, one word, you will send it to IO. So let's assume you are sending one word at a time. Let's assume what you are doing, you are sending one word at a time, one word at a time. Okay, yes or no? Because man memory can give you how much in one go? Can you tell me? The man memory can give you how much data in one access? Let me know. How much data can you get from the main memory? How much data can the CPU get from the main memory in one access? One word. Do you agree with me? Yes or no? So we want to transfer 100 words, but from main memory to CPU, one word will go. Yes or no? From main memory to CPU, one word will go. That one word CPU will put in the IO device. Okay, is this clear? So very simple. We want to transfer 100 words. Then what will happen? Very simple. This is the code. Okay, in this code, you can notice what is happening. Okay, we are checking the status. Remember, we are checking the status. See this. See this. Okay, we are checking the status word. The CPU is checking the status. Is the data ready? Okay, is the data ready? CPU is checking the status. So if the IO device is ready, remember memory is already ready. Do you agree with me? Because memory is very fast. Yes or no? Memory is very fast comparing to IO device. But we are checking, is the IO device ready? This is what we are checking. Please understand, we are not checking whether memory is ready or not, because memory is already ready. Memory is very fast comparing to IO device. IO device is slow. Okay, so this IO device has a status register. This has a status register, and the CPU is continuously checking, is the IO device ready for taking the one word? Yes or no? So remember, we want to transfer 100 words from main memory to IO. Then what the CPU will do? CPU will check, is the IO device ready to receive one word? This is what we are checking. This CPU is checking, is the IO device ready for receiving one word? Is the IO device ready for receiving one word? So we are continuously checking. Is this clear? We are continuously checking, is the IO device ready for receiving one word? Okay. Now, when the IO device is ready, then what we will do? Then we will transfer. Then the CPU will take one word from main memory and then it will transfer to the IO device. Okay. So like this. Again, for the next word, what will happen? Because we want to transfer 100 word. For the second word, what will happen? The same thing. For the second word, CPU will check, is the IO device ready to receive the next word? If the IO device is ready, then the CPU will do the transfer. Okay, then again the same thing will happen. Then the again same thing will happen for the next word. For the next word, CPU is checking, is the IO device ready for receiving the next word? Okay, if the IO device is not ready, then what will happen? If the IO device is not ready, then CPU will continuously check. If the IO device is not ready, okay, notice, if the IO device is not ready, then the CPU will continuously check. The CPU is continuously checking. So very simple. Now, if the IO device is ready, then CPU will take data from main memory and it will transfer to IO device. So like this, it will happen. Now tell me one thing. In this, during this 100 words of transfer, for how much time CPU is busy? Please tell me. During this 100 word of transfer, we are transferring 100 words. During this transfer, for how much time CPU is busy? For how much time CPU is busy? For how much time CPU is involved? Tell me, for how much time CPU is busy? Whole time, all the time. Very good, very good. A student is saying all the time. Yes, CPU is busy all the time. Remember, either CPU is checking the status bit or CPU is doing the transfer. But CPU is doing all the work. So CPU is all the time busy. Remember, CPU is all the time busy. Okay, either CPU is doing the useful work, means CPU is either transferring the data from main memory to IO, or the CPU is checking the status bit. But during the transfer, the CPU is all the time busy. So what is the advantage of this technique? The advantage of this technique, did you find some advantage of this technique? Let me know. Did you find any advantage of this technique? That is, the processor is in the full control. Yes or no? So the advantage of this technique, that is, processor is in full control. The IO devices are not in the control. The IO device cannot give the signal. The IO device cannot disturb. Okay, the processor is in the full control. The processor is running the program, and this program is in the full control of IO. So very simple. This is the idea, that the processor is in full control and does all the work. Tell me one thing. Very simple question I'm asking. You might be thinking, sir, processor is busy all the time. Then this is not a good method. Do you agree? You might be thinking, sir, processor is continuously busy, means processor is checking the status. Processor is not doing any useful work. Yes or no? So processor is wasting time. Okay, yes or no? The processor is wasting time. So this method is not good. Do you agree with me? This method is not good. Can you suggest one situation where this method will be best? Can anyone suggest any situation where this method will be actually best? Tell me. See, this method will not be good in the general purpose computer. In your computer, in my computer, in our general purpose computer, this method will not be good because there are other things to do. Yes or no? If the CPU is not wasting time, then CPU can do some other task. CPU can execute some other program. But notice, if you have, for example, washing machine, ATM machine, if you have these type of machines, then there you can use this. Yes or no? In the ATM machine, you can use this because remember, this is very safe. If you notice, because here the CPU is in the full control. Okay, you have written a program in the CPU, you have written a program. Now that program is in the full control. So this method, this program controlled IO, this is good in the ATM machine, in the washing machine, in these type of things. Do you agree with me? Because there is nothing else to do. In the ATM machine, if the CPU is not checking the ATM slot, see, okay, let's assume that no one is in the ATM room. Now, when no one is in the ATM room, CPU is continuously checking the ATM slot. Did someone insert? Did someone insert? Did someone insert? So CPU is continuously checking the ATM slot. Now tell me one thing, will you call it waste of time? In the ATM machine, if CPU is continuously checking the ATM slot, suppose CPU is continuously checking ATM slot, will you call it waste of time? Tell me. You will not call it waste of time. But the same thing, if it happens in your general purpose computer, will you call it waste of time? In your general purpose computer, if the same thing happens, will you call it waste of time? Yes, this is waste of time. Because in the general purpose computer, the CPU can do some other task. CPU can execute some other program. Yes or no? So CPU should not waste time in the general purpose computer. So in the general purpose computer, this method we do not use. So where we use it? We use it in ATM machine, washing machine, these type of things. Okay, but in the general purpose computer, we don't use this method. So remember, the advantage is CPU is in the full control. Okay, and CPU will do all the work. And what are the disadvantage? The disadvantage is that because of polling, the CPU is wasting time. Yes or no? A lot of time of CPU is consumed because of polling. because CPU is continuously checking the status. CPU is not doing any useful work. That is the reason a lot of time is wasted. Okay, read this. This paragraph is given in the Oxford course. Okay, see, this is very interesting paragraph. What this is saying? This is saying that this program controlled IO, this is inefficient. Do you agree? This program controlled IO. Yes or no? This programmed IO, this program controlled IO, this is inefficient. Do you agree? Yes, this is inefficient because CPU is wasting time. CPU is not doing any useful work. Yes or no? CPU is continuously polling. Okay, so CPU is wasting time. But you can see this efficiency is of no concern in the embedded system. What are the embedded system? In the embedded microcontrollers. Okay, for example, your ATM machine. For example, your ATM machine. Okay, means remember this inefficiency. This inefficiency matters in what? This inefficiency matters in general purpose computer. Yes or no? This inefficiency matters in general purpose computer. In general purpose computer. In our computer, in your computer, in my computer. Okay, yes or no? In general purpose computer, this inefficiency matters. Okay, because CPU is wasting time. But you can see in this ATM machine, this inefficiency, this is of no concern. Okay, because no one cares if the ATM machine is wasting time checking the buttons. Yes or no? Do you agree with me? We do not care if the ATM machine is wasting time checking the ATM slot. See, this is the idea that no one cares in the ATM machine. Case dispenser means ATM machine. Yes or no? Case dispenser. Case dispenser means ATM machine. So you can see no one cares whether the ATM machine is wasting time checking the ATM slot or not. Okay, because there is nothing else to do. After all, what it will do? Okay, if this ATM machine is not checking the ATM slot, then what else it will do? There is nothing else to do. Okay, so very simple. But remember, in the general purpose computer, this is a serious problem. This program controlled IO. Okay, this program controlled IO, this is a serious problem because it is wasting a lot of time. So that's it. Okay, so we have already seen everything. So you can see, can you hear me now? Can you hear me now? This is called polling. Continuously checking to see if the device is ready. This is called polling. Okay. So CPU is continuously checking to check whether the device is ready. This is called polling. Okay. CPU is wasting time here basically. If the device is not ready, let's assume device is not ready, then CPU is continuously checking. This is called polling. Okay. You can see CPU repeatedly ask if the device is ready, if the device is ready. Okay. So very simple. Now, tell me what is the solution? In the general purpose computer, this method is not good. Yes or no? This program control IO, this method is not good because CPU is wasting a lot of time. Then what is the what is the better method? Tell me. See, the better method is that, see this analogy. Okay, read this analogy. The analogy is like this. Let's assume you want your car to be fixed. Okay, now in this program controlled IO, what you will do? You will call the mechanic every minute and you will ask, is my car ready? Is my car ready? This is the idea of program controlled IO. Yes or no? You can call mechanic every minute. You are calling every minute. You are calling, is my car ready? Is my car ready? Is my car ready? This is the idea of programmed IO. This is the idea of programmed IO. Correct? Okay. Now, what is the better way? The better idea that is the mechanic will call you once it will be ready. Yes or no? The mechanic will call you once it will be ready. Do you agree? The mechanic will call you once it will be ready. You have given the task to the mechanic that please do this task. Now the mechanic will call you once the car will be ready. Okay. This is called interrupt driven IO. We will see this now. This is called interrupt driven IO. This is better. Do you agree with me? This is better because you are not wasting time. Notice one thing, in the programmed IO, you are wasting time. You are calling the mechanic every 1 minute. Every minute you are calling, is my car ready? Is my car ready? Is my car ready? So you are wasting your time. You are not doing any useful work. You are not doing any other work. Okay, but notice one thing. In this method, what will happen? In this method, the mechanic will call you when the car is ready. So during this time, what you can do? During this time, what you can do? You can do some other task. Yes or no? The mechanic will call you when the car will be ready. So during this time, what you can do? You can do some other program. You can execute some other program. You can do some other useful work. So this is called interrupt driven IO. This is our next topic, that is interrupt driven IO. Okay, so let's study this. Now let me tell you that interrupt driven IO, This concept we need to study for data transfer. Yes or no? Right now, what we are discussing? We are discussing data transfer between IO device and main memory. This data transfer we are discussing. So for this data transfer between IO device and main memory, now we need to see the next method. The next method is interrupt driven IO. But let me tell you one thing. This interrupt is a general concept. Okay, see, right now we are discussing data transfer, but other than data transfer, this interrupt is a general concept. Let me tell you. Okay, so let's assume the some device. Let's assume in your computer. Let's assume there is a device which does not want to do data transfer, but still it can send interrupt signal. Okay, what I'm saying right now our focus is on the data transfer between IO device and main memory. This is what right now we are discussing. How to do data transfer between IO device and main memory. For this, we need to study the next method, that is interrupt driven IO. But I am telling you that interrupt is a general concept. Interrupt is a general concept. Means other than data transfer, also this concept is used. Okay, other than data transfer, you can use this concept. Okay, is this clear? So very simple thing. I told you that interrupt is a general concept. You can use it for data transfer, or you can use it for many other things. Okay, you can use it for many other things. So right now what we will do, we will focus on the data transfer. Right now we will study interrupt driven IO for data transfer. Later we will study interrupt in general. Okay, so right now our focus will be on the data transfer. Remember, our focus is on the data transfer between IO device and main memory. Okay, so this method we will see, and after some time we will see the interrupt concept in general. Okay, is this clear? Now, let me tell you this interrupt driven IO data transfer analogy. What is the analogy? The analogy is very simple. If I give you some task to do, okay, let's assume you are the mechanic. I give you my car that please fix it. Then I will not ask you continuously, is my car ready? Is my car ready? Is my car ready? I will not do that. What I will do, I will give you the task. I will give you my car that please fix it. Okay. Then what I will do, I will go and I will do some other useful work. Okay. I will do some other program. I will execute some other program. I am doing some other useful work. Now what you will do? Now notice what you will do. I am executing some other program. I have given you the task. Okay, after giving you the task, I'm not wasting time. What I'm doing, I'm executing some other program. This is some other program that I'm executing. Okay, some other useful work I'm doing. Now I'm doing this work. Now let's assume the car is ready. Then what you will do, you will come to me. Okay, you will tell me that yes, car is ready. Is this clear? When the car is ready, then you will come to me and you will say that car is ready. Then what I will do, let's assume I will stop this task. Okay, I will stop this task. What I will do, I will check, is the car ready? Okay, I will check. Okay, is the car ready? I will check my car. Yes or no? Definitely, I will check my car that yes, car is ready. Okay, I will check my car. And then if the car is ready, then what I will do, after checking whether the car is ready, then what I will do, then I will continue my execution. Okay, is this clear? Then I will continue what I was already doing. So this is the idea. Is this clear? Please tell me, did you understand? So the analogy is very simple. If I give you some task, then after giving you some task, I will not waste my time asking, is it ready? Is it ready? Is it ready? What I will do, I will go and I will do some other work. Okay, I am executing some other program. Now you will come to me, you will say the task is ready. Then what I will do, I will stop my work. Okay, I will save my work. Basically, what work I was doing, this work I will save. I will save it, and then what I will do, I will check. Okay, did you do my work? Okay, then I will check. Yes, 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 yes. You have done it. Okay, you have done it. Then I will continue my previous work. Yes or no? I will continue my previous work. So this is the interrupt driven IO. Did you understand? Please tell me. So here, remember, the CPU is not continuously checking, is the device ready? Is the device ready? Is the device ready? The CPU is not continuously checking. When the device will be ready, when the data will be ready, then the interface will generate the interrupt signal. Okay, is this clear? The interface, this will generate the interrupt signal. It will say, the interface will say that the data is ready. Now when the data will be ready, then CPU, what it will do, then the CPU will take this data, it will put it in the CPU register, then from it will put it in the main memory. So this is what it will do. Okay, so did you understand? Okay, let me know. So now let's see this interrupt driven IO. Now let me explain this. The idea is like this. Okay, understand this interrupt driven IO. Interrupt driven IO data transfer. We are interested in data transfer right now. Yes or no? After some time, we will see interrupt concept in general. Okay, but right now our focus is on the data transfer. We will only do data transfer between main memory and IO device. So this is what we need to study right now. So what will happen? Very simple. This is the idea that CPU, what it will go, will what is the first step? Tell me, what is the first step? The first step is CPU will give the command to the interface. Yes or no? Okay, CPU will give command to the interface. This is the first step. CPU will give command to interface. Let's assume for example, if I give you some task, okay, then I will give you command to do the task. Yes or no? So the first step is command will be given to the interface, okay, to the IO interface. This command will go. Now there is IO interface here. Okay, there is a IO interface here. This is IO module. You can call it IO interface or you can call it IO module. Both are same. Okay, is this clear? So there is IO interface here. So you can see the CPU will give command to the IO interface. Now what this IO interface will do? Okay, after giving this command, remember the CPU will give this command to the IO interface. Then after this giving this command, what the CPU will do? CPU will execute some other program. Is this clear? CPU will execute some other program. This is some other task. This is some other program. CPU will execute some other program. Means CPU will do some useful work. Okay. So this is the second thing. Remember, first CPU will give the command to the interface. Okay. Then the second thing, then the second step is CPU does some other work. CPU does some other useful work. Some other useful work. Okay, is this clear? CPU will not waste time in checking the status register. Okay, now remember, when the command will come to the IO interface, now what the IO interface will do? What is the third step? Tell me. When the command will come to the IO interface, what is the third step? The IO interface will collect data from the IO device. Yes or no? Do you agree? From the IO device, from this IO device, what the third step? The third step is this IO interface will collect data. Collect data from IO device. Okay, and where it will store it? Where it will put it? This data that is coming from the IO device, where it will put it? In the interface, we have buffer, we have data register. Yes or no? So there is data register. There is data register. So here it will put the data. Okay, the data is slowly coming. Okay, the data is slowly coming, and the data will be put here. Okay, yes or no? And there is status register also here. There is status register also here. This is the status bit. This is the status bit. Now remember. So during this time, when this data is coming to the interface, what CPU is doing? Tell me. What CPU is doing during this time when IO device is giving the data to the interface? Okay, during this time, what the CPU will do? CPU is doing some other useful work. Remember, CPU is not wasting time. CPU is not wasting time. CPU is doing some other useful work. I told you, this is interrupt driven IO. This is interrupt driven IO. This is not program controlled IO. Okay, CPU is doing some other useful work. CPU is already executing some other program. Some other program CPU is already executing. Okay, yes or no? So you can see this data will be collected by the IO interface. Now, when the data will be ready, what the interface will do? Now let's assume the data is ready. The data is ready. Now, when the data will be ready, then what the interface will do? The interface will make it one. Yes or no? When the data is ready, then the interface will make it one. Now, what will happen? When the interface will make it one, when the data is ready, then what the interface will do? Interface will send a interrupt signal to the CPU. Okay, this is the next thing. When the data is ready, then the interrupt signal will be sent. Interrupt control signal. There is a interrupt control signal. There is a control signal, interrupt control signal. So this device, this interface will send interrupt control signal to the CPU. Okay. Now what the CPU is doing? Notice one thing. CPU is already executing some other program. Do you agree? CPU is already executing some other program. So let's assume CPU is executing this instruction. See, let's assume CPU is executing this instruction. This instruction is like this. Now, after executing the half instruction, will the CPU stop the half instruction? Will the CPU stop the half instruction? No, CPU will execute this instruction. CPU will execute completely. After executing this instruction, the CPU will check, okay, the interrupt signal has come. Yes or no? Remember what I'm saying? I'm saying that let's assume CPU is executing some other program. Yes or no? Now the interrupt signal has come. Okay. At this time when CPU is executing this instruction, in the middle of this instruction the interrupt signal has come. Then CPU does not care. CPU does not care. The CPU will execute this instruction completely. After executing this instruction completely, now the CPU will check, okay, the interrupt signal has come. Okay, now when the interrupt signal has come, now what the CPU will do? Now the what is the fifth thing? Now the CPU will save the work. Yes or no? This work that CPU is doing, this program that CPU is executing, the CPU will save this work. Yes or no? Because CPU does not want to destroy this work. We do not want to destroy this work. So what the CPU will do? CPU will save this work. Okay, it will save this work. After saving this work, what CPU will do? Now CPU will take this data, CPU will put it in the register, then from the register to the main memory. Is this clear? Again, did you notice one thing? That again the CPU is involved. Okay, for the actual data transfer, who is involved? Tell me. For the actual data transfer, who is involved? Who is doing the data transfer? Again, the CPU is doing the data transfer, remember. Okay, but CPU is not wasting time when the data is being ready. This is the difference. This is the only difference. Okay, remember in the programmed controlled IO, there CPU is wasting time when the data is being ready. Okay, when the data is being ready, then CPU is wasting time. But in this interrupt driven IO, CPU is not wasting time when the data is being ready. Okay, when data is being ready, CPU is already executing some other program. Okay, now when the data will be ready, then the interface will generate an interrupt signal. This interface, it will send an interrupt signal. Now what this CPU will do? CPU will execute the this instruction, this current instruction, whatever CPU is doing, CPU will execute this instruction at least. Okay, after executing this instruction, CPU will see, okay, interrupt signal has come. Now what the CPU will do? CPU will take this data from the data register. CPU will take this data, CPU will put it in the CPU register. Then from the CPU register, the data will go to the main memory. Okay, is this clear? Now, after this data transfer is over, see, from the data register, the data will go to the CPU register. The CPU will put it in the main memory. Now, this data transfer is over. Once the data transfer is over, now what the CPU will do? Tell me. Once the data transfer is over, from here to main memory, the data transfer is over. CPU has done the data transfer from here to main memory. Now, after doing this data transfer, what the CPU will do? CPU will continue this program. Yes or no? CPU will continue executing this program. Very simple. I hope you understood. Is this clear? So, very simple. Did you understand this? Please tell me. So let's read state. See, these are the steps. Okay, let's read this. You will understand this. Interrupt driven data transfer. We want to do data transfer, okay, between IO device and main memory. Now let's take example of, let's assume you want to read from the IO. Okay, means let's assume that you want to read from the IO. From IO device, you want to send data to the main memory. Then what the first step? Read the first step. The first step is the CPU will initiate the data transfer. Yes or no? CPU will initiate the data transfer by issuing a command to the IO module. This is the first step, you already know. Okay, I told you this is the first step, that CPU will send the command to the IO module. Okay, and then what the CPU will do? After sending the command to the IO module, what the CPU will do? The CPU will do some other work. Means CPU can execute some other program. Okay, yes or no? Now what the IO module will do? What the IO module will do? IO module, when it will receive the request, yes or no, this IO module, when it will receive the command. So IO module, when it will receive the command, then what it will do? It will read the data from the IO device. Yes or no? It will collect the data from the IO device. So very simple, this IO module, when it will receive the command from the CPU, then what this IO module will do? It will read the data from the IO device. It will collect the data from the IO device. Now you can notice, when the data will be ready, in the data register, when the data will be ready in the data register, then what it will do? Basically, the IO module is ready for data transfer. Okay, from the IO device, the IO module, the IO interface has collected the data in the data register. Now, when the data is in the data register, what this IO module will do? It will signal, it will send an interrupt signal to the CPU. It will send an interrupt signal to the CPU. Is this clear? Very simple. Now, what CPU will do? Now, what CPU will do? Remember? So you can see CPU will execute the current instruction. Yes or no? CPU is already doing some work. CPU is already executing instructions of some other program, yes or no? So the CPU is executing some instruction, it will complete that. Okay, it will complete that instruction. Okay, that instruction which CPU is executing, it will complete that instruction. At the end of that instruction, what the CPU will check? CPU checking the interrupt signal has come. Okay, the interrupt signal has come. There is a pin actually in the CPU, there is a pin, let me tell you. In the CPU there is a pin, there is a pin for interrupt. Okay, INTR. Okay, is this clear? There is a pin in the CPU. In the CPU, there is a pin. There is a pin. So this CPU will check that this pin is one. Okay, means the interrupt has come. Is this clear? So you can see the CPU will execute the current instruction. After executing the current instruction, the CPU will check the interrupt has come. Now, when the interrupt has come, now what the CPU will do? When the interrupt has come from the IO module, now what the CPU will do? CPU will save the current work. Yes or no? Do you agree with me? Processor will save the current work. Processor will save the current work, means the current program the CPU will save. Okay, means in the current program the CPU will save the program counter, the program register. So basically all these things CPU will save. Basically CPU will save the current work. After that, what it will do? After that, it will process the interrupt. What it means? Process the interrupt. What it means? Process the interrupt. It means processor will read the data from the IO module and it will store in the main memory. Processor, what it will do? It will read the data from the IO module and then it will store it in the main memory. Okay. After this is over, after this data transfer is over, then what the CPU will do? CPU will continue its previous work. Yes or no? Okay, after the data transfer is over, then CPU will continue its previous work. Okay, is this clear? Very simple. So this is the step by step this idea. Let me know this technique we have seen step by step. Please tell me, did you understand? So we have seen everything. Now remember one thing here, that CPU is not wasting time checking the status bit. Yes or no? This is one important point, that when the data is being ready, see, IO interface is collecting data from the IO device. Yes or no? IO device is very slow. Slowly the IO device is giving the data. Now the IO interface is collecting data from the IO device. Now during this time, remember, during this time, CPU will not waste time checking the status. Okay, is this clear? What CPU will do? CPU will execute some other program. Okay, but here, is there any overhead? Is there any waste of time? Can anyone tell me? In this technique, is there any waste of time? Can anyone suggest? In this technique, is there any waste of time? Can anyone suggest? Can anyone suggest, is there any waste of time in this technique? Yes, there is waste of time in this technique. See, the waste of time is here. When the interrupt will come to the CPU, then CPU is already executing some program. Notice one thing. Notice one thing. CPU is already executing some program. Okay, some programs. And at this time, let's assume interrupt comes. At this time, interrupt comes. At this time, interrupt occurs. So, okay, is this clear? CPU is already executing some other program. This is some other program. This is some other program. Okay, so program is like this. Program is like this. Now remember, when CPU is executing this, CPU is here. Then interrupt occurs. Now what the CPU will do? Now there is waste of time. See, the waste of time is like this. Now CPU will save this work. That is the waste of time. Yes or no? CPU needs to save this work. Do you agree with me? CPU will save what is the program counter, because after this data transfer is over, CPU need to execute the next instruction. Do you agree with me? See, when the CPU is executing this instruction, then interrupt has come. Okay. Now, when the CPU will do the data transfer, then what the CPU need to do? After doing the data transfer, CPU need to start from here. Yes or no? CPU will resume here. So here the CPU will resume. Okay. Here the CPU resumes. Resume point of CPU. Correct? Here the CPU will resume. So what the CPU need to do? CPU need to save the program counter. Do you agree with me? CPU need to save this work basically. What's work CPU is doing? This work CPU need to save. CPU need to save the program counter. Okay, maybe registers also. Because during the execution of this program, maybe some registers, the flag register, yes or no, there is flag register, there are other registers. So basically, CPU will save this work. Okay, after saving this work, CPU will go and CPU will do the data transfer. Okay, so remember, there is a context switch here. Did you notice? Okay, here interrupt occurs. Now after this interrupt occurs, what it will do? The CPU will go. Okay, now after this, what the CPU will do? CPU will do the data transfer. Is this clear? This data transfer CPU will do. this data transfer CPU will do. Okay, this data transfer will be done by CPU, will be done by CPU. Is this clear? Okay, so this data transfer will be done by CPU. What it means? It means, okay, from the IO buffer, the data transfer will happen like this, that from the IO buffer, the data will go to the CPU, and from the CPU, the data will go to the main memory. Okay, so you can easily see that this data transfer will be done by the CPU. Okay, so did you notice there is a context switch here? There is a context switch here. Okay, CPU was executing this program. At this moment, the interrupt occurs. Now, when the interrupt occurs, then what the CPU will do? Then CPU will do the data transfer. Yes or no? But after completing this data transfer, CPU must resume here. Yes or no? CPU must resume here. So for that reason, what it will do? Before doing the context switch, remember the CPU will save this program. CPU will save this work. Yes or no? So what the CPU will do? CPU will save the register. CPU will save the program counter, because program counter should be pointing here. So that is the reason. So remember, when the interrupt will come, then CPU will save the program. This saving the program, this is overhead. Okay, is this clear? This context switch is the overhead. Okay, is this clear? Please tell me. This context switch and saving the program, saving the register, saving the program counter, this is the overhead. This is the, I can say, wasted time. This is the time where CPU will be wasting time. Okay, is this clear? Now, what the CPU will do? CPU will do the context switch. CPU will do the data transfer. After completing this data transfer, where the CPU will go? After completing the data transfer, where the CPU will go? After completing this data transfer, CPU will go and resume this. Okay, is this clear? So very simple. So remember here, what is the time wasted? Where is the time wasted? Time wasted in interrupt driven IO. In interrupt driven IO. So where is the time wasted? You can say time wasted, or you can call it overhead. Or you can call it overhead. So what is the time wasted? Where is the time wasted? Very simple. Saving the work. Yes or no? Saving context. Saving context, or I can say saving work before jumping to data transfer. Before jumping to IO memory data transfer. Correct? So this is saving work. Okay, you will save the work. What, when I say saving work, what it means? It means you are saving the registers, you are saving the program counter, these things you are saving. So you will save the work, okay, before jumping to the data transfer. Then, okay, then there will be context switch. Then there will be context switch. Yes or no? There will be context switch. Basically, from, remember, from this program you will go to this program. This is the point. Okay, is this clear? So you can say this is a program. This is also a program for data transfer. So basically, from this program you will jump to this program. So this is called context switch. Okay, is this clear? This is called context switch. So this is the overhead. Some time will be wasted here. This is what is written here. You can read this, that CPU time is required, okay, only during data transfer. That you already know, that CPU will do the data transfer. Okay, there will be some overhead for context switch and returning, okay, when you come back. So there will be some overhead. So I have already told you that saving the work and doing the context switch. Okay, and there will be another context switch. Do you agree with me? There will be another context switch. This is the context switch from current program to the data transfer. Yes or no? To the data transfer program. To the data transfer program. Now, when this will be over, then again what you will do? Then again you will restore. Then again you will restore the previous program. The previous program. Okay. So this is the idea. So very simple. So this is the waste of time. Other than that, there is no waste of time. Very simple. So we have seen what is interrupt driven IO. See this diagram. This diagram will explain everything that we have seen. Okay. So the CPU will give command to the IO module. Yes or no? CPU will give command to the IO module. Then CPU will do something else. Remember, CPU will give command to the IO module, then CPU will do something else. CPU will execute some other program. Now the IO module will collect the data. Yes or no? The IO module will collect the data. Remember the IO module, it will collect the data from the IO device. It is collecting the data. Now when the data will be ready, now remember when the data will be ready, then what the IO module will do? When the data will be ready, then what the IO module will do? It will generate interrupt signal. When the data will be ready, then IO module will generate the interrupt signal. Okay, so the interrupt will go from IO to CPU. The interrupt signal will go from IO to CPU. Okay, now you can see now what the CPU will do. Now CPU will do the data transfer. IO to CPU, CPU to main memory. So the CPU will do the data transfer. Okay, if the data transfer is complete, then that is good. If the data transfer is not complete, then the same thing will repeat. Okay, so this is the idea. So we have seen everything, all these points, everything you can easily see. Look at this diagram. See, I told you that CPU will give command to the IO module. Yes or no? Okay. So remember, the CPU is giving command to the IO module. Now what the IO module is doing, it is collecting the data from the IO device. This is your IO controller. Okay. Remember, this is your IO controller. This is the IO controller. Remember here. So here, remember, the IO controller, it will collect the data from the IO device. There is data register, there is status register. So these type of registers are there. Now, when the data will be ready, here, when the data will be ready, then interrupt signal will go, okay, to the CPU. And then the CPU will do this data transfer. Then CPU will take this data and then it will put it in the main memory. So very simple. Now let's move on. So we have seen what is programmed IO and what is interrupt driven IO. Did you understand both of them and did you understand their differences? Please tell me. Are they crystal clear? Please tell me. Are they crystal clear? What is programmed IO? What is interrupt driven IO? Are they crystal clear? Please tell me. Let me know. Anyone has any doubt in this? So we have seen interrupt driven IO. Also we have seen programmed IO. These two things we have seen their differences. Okay, now what we are going to do, we are going to solve a lot of questions. Okay, so let's start now. Whatever you have understood, just apply your knowledge and solve all these questions. All these questions are standard questions. So let's start. Let's solve this question. This is Berkeley question. You can see question number 1. Tell me what the answer. How many interrupts will be required to read 100 byte of input? We want to read 100 byte of input, 1 byte at a time using polling based IO. Please tell me what the answer. Read the question and tell me the answer. Pause the video and please write your answer in the comment right now. Okay, think about this question, pause the video, write your answer in the comments, then you play the video and then you check your answer. Okay, then you see whether your answer is correct or not. Do it. See, read the question. Which IO mechanism are you using for data transfer? Which mechanism are you using for data transfer? Please tell me. For IO to main memory data transfer, which mechanism you are using? You are using polling based IO. That means programmed IO. Yes or no? You are using programmed IO. Programmed controlled IO. Okay. In this programmed controlled IO, is there any concept of interrupt? In this programmed controlled IO, does the device send interrupt? In the programmed controlled IO, will the interface send interrupt? Please tell me. Will the IO device inform the CPU? Please tell me. In the programmed IO, will the IO device inform the CPU? Will it send interrupt to CPU? No, it will not happen. Do you agree? So the question is asking how many interrupts will be required to read 100 bytes of input 1 byte at a time. The answer will be 0. Okay, no interrupt. The answer will be 0. In the programmed IO, okay, there is no interrupt concept. There is no interrupts. I told you that device, the IO device or the IO interface will not inform the CPU. Do you agree? We have already seen this. In the programmed controlled IO, the IO device, the IO interface, that will not inform the CPU, that will not send interrupt to the CPU. The CPU will continuously check the status of the interface. Is this clear? The CPU is continuously checking the status of the status register. So here remember, no interrupt will be generated. No interrupt will be generated, so the answer will be 0. Did you understand this question? A beautiful question, right? Many students, they will answer 100. See, read the question carefully and then you answer. Did you understand this? Please tell me. Did you understand this first question? So for the first question, the answer will be 0. What about the second question? Tell me. What about second question? How many interrupts? Please tell me which mechanism are we using for the data transfer between IO and memory in the second question. Let me know which mechanism are we using to transfer data between IO and main memory. That is interrupt driven IO. Yes or no? This is interrupt driven IO. Now what the question is saying? The question is saying how many interrupts will be required to read 100 bytes of input. We want to read 100 bytes of input 1 byte at a time. How many interrupts will be required? Tell me. How many interrupts will be required? We want to read 100 bytes but 1 byte at a time. So how many interrupts will be required? The answer will be 100. Yes or no? Is this clear? See, what will happen? Very simple. In this case, what will happen? We are reading one byte at a time. Please read this. Read this, what we are saying. We are saying 1 byte at a time. We are reading 1 byte at a time. See, this will happen. Notice. Let me tell you the complete picture. Quickly, you will understand. So the CPU want to read 100 byte from the IO device. This is your IO device. Quickly see. Okay, this is your IO device and this is the interface. Correct? Okay, this is the interface and this is the CPU. Now, what this CPU is doing? CPU is giving command to the interface that I want to read 100 bytes. Okay, yes or no? So the command is going to the interface. Now, when the command will go to the interface, then CPU will execute some other program. Yes or no? Correct? Now, see, first the command will go. Okay, yes or no? The command will go. So the CPU will send command to the interface that I want to read 100 bytes. Okay, give me 100 bytes. So this command will go to the interface. Okay, now after that, what CPU will do? CPU will execute some other program. CPU is executing, CPU is doing some other work. Okay, now what is the third thing? Tell me what is the third thing? Now interface will collect data. Yes or no? The third thing, interface is collecting data from the IO device. Yes or no? So interface is reading data from the IO device and interface is putting the data in the buffer, in the data register. Yes or no? Now during this time, when the interface is collecting data from the IO device, during this time, CPU is executing some other program. CPU is doing some useful work. Yes or no? Now notice, now the question is saying that we are reading 1 byte at a time. Okay, we are reading 1 byte at a time we are reading. What it means? It means that this IO device, it will give 1 byte. This IO device, it will give 1 byte. Now when the 1 byte will come, what the interface will do? What the interface will do? It will make the status bit 1. Yes or no? This status bit will become 1 because you can see from the IO device 1 byte has come. Now when the 1 byte will come, then what this interface will do? It will make this status bit 1 because there is a status register. So this is your status register. In the status register, this status bit will become 1. Now what the next step? The next step, fourth step. The fourth step is that this interface will send interrupt to the CPU. Yes or no? It will send interrupt signal. It will send interrupt signal to the CPU. Okay, now what the CPU will do? CPU will execute the current instruction completely. Okay, after executing the current instruction completely, what the CPU will do? CPU will save the work. Yes or no? CPU will save what it is doing. CPU will save it. Then CPU will do context switch. Okay, and then CPU, what it will do? Okay, in the context switch, CPU will do the context switch and CPU will transfer this data. This 1 byte data, remember, from the data register, this 1 byte will go to the CPU. This 1 byte will go to the CPU and from there it will go to the main memory. Okay, is this clear? So remember this 1 byte, you can notice this 1 byte will go to the CPU in the CPU register and from there this 1 byte will go to the main memory. So this is what will happen for 1 byte. Okay, yes or no? Because the question is saying we are reading 1 byte at a time. But is the task over? Please tell me, is the task over? Let me know. Is our task over? Our task is not over because we need to read 100 bytes. Yes or no? So now what the CPU will do? Again, what the CPU will do? Again, CPU will give the command, remember, for the next byte. Because remember, the IO device will need time to prepare the next byte. Yes or no? IO device is very slow. Very slowly it is giving the data to the interface. So again, the same thing will happen, remember. For the second byte, for the next byte, again the same thing will happen. Again, remember, the same thing will happen. The CPU will give the command. Okay, again the interface will take the data from the IO device. During this time, CPU will again execute this program. Okay, CPU will again execute this program. Now, when the IO device will give 1 byte, then interface will give interrupt signal to the CPU. CPU will save this work. After saving this work, CPU will do the data transfer. Okay, the next byte CPU will transfer to the main memory. Now, 2 bytes we have transferred. Yes or no? For 2 bytes, so far, how many interrupt signal were generated? So far, we have transferred 2 bytes from the IO device to main memory. How many interrupt signal have been generated? Two interrupt signal have been generated. Now, for the next byte, what will happen? Is our task over? Our task is not over. We need to send the third byte. Again, the same thing will repeat. Again, CPU will give command to the interface. Okay. Again, after giving the command, the CPU will execute some other program. CPU will do some useful work. Okay. Then this interface will collect next byte from the IO device. This next byte will come to the interface. After this byte will be ready in the interface will generate an interrupt signal. When the interrupt signal will go to the CPU, what the CPU will do? CPU will execute this instruction fully. This instruction fully it will execute. After that, CPU will do context switch. CPU will save this work. Okay, CPU will save this work, and then CPU will do the data transfer. CPU will take this byte to the CPU register. From the CPU register, it will send it to main memory. Okay. Now 3 bytes are over. For 3 bytes, 3 interrupt signal were generated. Similarly, for 100 byte, 100 interrupt signals will be generated. Is this point clear? So please tell me, are these two questions clear to everyone? These are Berkeley University questions. They can come in the GATE exam also. Okay. I hope these two questions, I hope they come in the GATE exam. Many students will make mistake in the first question. In the first question, many students, they will answer 100, but the answer is 0. In the second question, the answer is 100. Is this clear? Please tell me. These two questions, are they clear? Crystal clear to everyone? Let me know. These two questions, are they crystal clear to everyone? So remember, you can see this is the answer given by the Berkeley. These are the answers given. You can see for this question, the answer will be 0 because polling does not use interrupts. Read this. Polling does not use interrupts. Okay. And for the second question, answer will be 100, one for each byte. Okay. One interrupt signal will be generated for each byte. Tell me the answer for this question. This is GATE CSE 1990 question. State whether the following statement is true or false. The data transfer between memory and IO device using programmed IO is faster than interrupt driven IO. Is this true? The data transfer between memory and IO device using programmed IO that is faster than interrupt driven IO. Is this statement true? This statement is false. Yes or no? Because usually interrupt driven IO is better. I told you, yes or no? We have already seen that. Usually, this interrupt driven IO, this is actually usually better. See, programmed IO, in this programmed IO, CPU will waste a lot of time. Okay, yes or no? CPU will waste a lot of time. But remember, in the interrupt driven IO, CPU will do some useful work. Okay, in the programmed IO, the CPU will continuously check, is the data ready? Is the data ready? Is the data ready? Okay, but in the interrupt driven IO, the CPU will not check whether the data is ready or not. The CPU will execute some other program. Okay, and when the data will be ready, then the IO interface will generate an interrupt signal. And when the interrupt signal will come to the CPU, then what the CPU will do? Then CPU will do the data transfer. Yes or no? So remember, usually the interrupt driven IO that is better. Okay, so this statement is saying programmed IO is faster than interrupt driven IO. This statement is a false. Okay, is this clear? Because remember, you can see that interrupt driven IO, this is generally better than programmed IO. Is this clear? Interrupt driven IO, this is generally more efficient than programmed IO in reducing CPU idle time. Okay, in reducing CPU idle time. Okay, very simple. Now, one interesting question from the Waterloo University. This is very interesting question, and I hope this question comes in the GATE exam. Read this question. This is from Waterloo University. 1C. The question is saying interrupt driven IO is always faster than programmed IO. Is always faster than programmed IO. Is this statement true or false? Interrupt driven IO is always faster than programmed IO. Is this statement true or false? Please tell me. Let me know. Interrupt driven IO that is always faster than programmed IO. This statement is false because of always faster. See, interrupt driven IO is usually faster, that is correct. Okay, if I say generally faster, okay, if I say usually faster, that is correct. Usually faster, that is true. Usually faster, that is true. But this is saying always faster. This statement is false. Can you give me one situation where interrupt driven IO will be slow and programmed IO will be fast? Anyone want to give me one situation? Give me one situation where programmed IO will be fast and interrupt driven IO will be slow. Anyone? Can anyone think about one situation? Let me give you the example. Think about small frequent data transfers. Okay, think about this situation. See, think about this situation that there is IO device which is very fast. This IO device, let's assume this is very fast. Okay, let's assume this is very fast, but this will give, see, this is very fast, but this is giving 1 byte at a time. Okay, just think about this situation. I'm saying there is a IO device which is very fast. Okay, but this is giving 1 byte at a time. Okay, 1 byte at a time you are getting, 1 byte at a time. Let's assume this is your interface. This is the interface. Okay, and let's assume you are getting 1 byte at a time. Basically, when the 1 byte will come here, then the 1 byte you need to store in the main memory. Is this clear? We are storing 1 byte at a time in the main memory. Is this clear? Now, in this situation, notice one thing. This IO device is very fast, but it is giving 1 byte at a time. Okay, when this 1 byte will be given, then the next byte will immediately come. Okay, but 1 byte at a time, this IO device is giving you, and this 1 byte you are saving in the memory. Then tell me, the interrupt driven IO, what it will do? Notice what interrupt driven IO will do in this situation. What interrupt driven IO will do? Tell me. In this situation, notice when the 1 byte will come, then what will happen? When first byte will come, for the first byte, what will happen? Interrupt will be generated. Context switch will happen. Do you agree with me? Do you agree with me? There will be context switch. Yes or no? See, notice one thing. I am saying that this IO device is very fast. It is giving 1 byte very quickly. Okay, 1 byte, 1 byte, 1 byte. But when the 1 byte will come, then you have to store it in the main memory. Means we are storing 1 byte at a time. Okay, we are transferring 1 byte at a time. But the IO device is very fast. Now, when the 1 byte will be ready in the interface, then what this interrupt driven IO will do? When the 1 byte will be ready, then in this interface will generate the interrupt signal. The interrupt signal will go to the CPU. What the CPU will do? CPU was doing something. Yes or no? CPU was doing some other work. CPU will stop that work, and the CPU will do this data transfer. Okay, and for that, basically, what the CPU will do? Remember, CPU will stop this work. CPU will save this work. CPU will save this work. After saving this work, CPU will do the data transfer, and after that, it will resume this work. Okay, yes or no? So there is a context switch. Okay, when the interface will generate a interrupt signal, CPU was already executing some program. Now the CPU need to do context switch, because CPU need to do this data transfer. CPU will take this 1 byte, put it in the CPU register. From there, it will put it in the main memory. Yes or no? So this is what the CPU will do. Agree? So you can easily see that in the interrupt driven IO, for every byte, what is happening? In the interrupt driven IO, just visualize this concept. Remember, in the interrupt driven IO, for every byte, what is happening? For every byte, what is happening? Context switch is happening. Yes or no? Context switch is happening. For every byte, context switch happens. For every byte, you are saving the work, saving current work. Correct? Okay, so these things you are doing for every byte, But remember, okay, you will do context switch, you will save your current work, these things you will do, but immediately the next byte will come. Just think about it. Immediately the next byte will come. Again, the same thing. Again, immediately what you need to do? Again, you immediately need to save your work. Again, you control. Again, you do context switch. Now, immediately the next byte will come, because this IO device is very fast. Immediately the next byte will come. When the next byte is coming, again, what you will do? Immediately the same thing. You will save the current work. You will do the context switch. Are you getting my point? That if the IO device is very fast, but it is giving you small data. Okay, the data is that it is giving you small. See, small data it is giving you at a time, but device is very fast. Means what I'm saying, think about small frequent data transfers. Is this clear? Think about small but frequent. Small but frequent. Think about small but frequent data transfers. Okay, is this clear? In this type of situation, interrupt driven IO is wasting a lot of time. Are you getting my point? Please tell me. In this situation, the interrupt driven IO, this is very inefficient in this situation. Okay, what will happen in the programmed IO? Tell me what will happen in the programmed IO. What will happen in the programmed IO? In the programmed IO, there is no concept of context switch. Yes or no? In the programmed IO, there is no concept of interrupt. There is no concept of context switch. There is no context switch. Okay, there is polling. There is no concept of context switch. There is polling. There is polling. Yes or no? So now notice one thing. See, the IO device is very fast. It is giving you one byte very fast. Yes or no? Now notice one thing. The polling is actually good here. In this situation, do you agree that polling will be good? Okay, because the IO device, see, the IO device is continuously checking the status. Now, because the IO device is very fast, sorry, CPU is continuously checking the status. This is the status. Notice. CPU is continuously checking the status. CPU is continuously checking the status, but the IO device is very fast. So immediately this status will become 1. And when the status will become 1, then the CPU will do the data transfer. After you do the data transfer, immediately this will become 1. So, okay, because this IO device is very fast, this status bit will remain 1. Yes or no? See, when the CPU will do the data transfer, at that point, another 1 byte will come. When the CPU is sending this 1 byte, another 1 byte will come. So are you getting my point that here the polling is actually useful? Yes or no? Here polling is actually a useful, very useful, because the device is very fast. If the IO device is very fast, then polling is actually useful. Is this clear? Please tell me. So remember, for very fast devices, this is what I'm saying. For fast devices, for fast IO devices, remember, for fast IO devices, polling is actually better. Polling is better than interrupt driven, or I can say polling is efficient. Polling is faster, or I can say more efficient. More efficient than interrupt driven IO. Then interrupt driven IO. Okay, is this clear? Please tell me. So when you have fast devices but small data at a time, okay, means in this type of situation, basically small but frequent transfers, but frequent fast transfers, frequent transfers. Okay, in this type of situation, polling is actually faster. Can you visualize this? Please tell me. See, just think about it. Okay, let's take the real world scenario. Okay, in the real world scenario, let's assume you are at your house. Okay, and someone is giving you maybe one brick at a time. See, it's like this. Okay, just notice one thing, that have you seen this type of situation in the construction? When some people are doing construction, then this person will give the brick. Okay, this person will give the brick to the next person. Okay, to the next person. Let's assume you are here. This is you. Okay, so this person is giving you brick, okay, in the construction work. Yes or no? Now notice one thing. If this person is very fast, just think about it. If this person is very fast, he's quickly giving you one brick at a time. Okay, one brick, one brick, one brick, one brick. Yes or no? Okay, it is giving you very fast. Okay, let's assume this person is very fast, but one brick at a time he is giving you. One brick at a time. Now in this situation, do you notice that in this situation, polling method is actually good, because there is no context switch, there is no interrupt, nothing. Yes or no? Okay, the one brick will come. The one brick will come. You will put it in the main memory. Okay, yes or no? So you can see one brick will come. You will put it in the main memory. Now, when you are putting in the main memory, another brick will come. You will put it in the main memory. When you are putting it in the main memory, another brick will come. So you can see that it is actually good. Polling is actually good here. Yes or no? In this situation, did you notice that polling is actually better method? Polling is here efficient. Okay, now notice about interrupt driven IO. Now in this situation, think about interrupt driven IO. See, interrupt driven IO, what it will say? It will say that now in the interrupt driven IO, what this processor will do? It will do some other work. Just think about it. It is going to do some other work. Immediately one brick will come. Okay, yes or no? Now again, what it will do? It will save this work. It will save this work, and it will take this brick and it will send it to the main memory. Then again it will go and again it will do some work, but immediately the next brick will come. So you can see this context switch is happening, yes or no, very frequently, very immediately the context switch is happening. Okay, yes or no? So because of this context switch, time is wasted basically. Okay, in this situation here, this interrupt driven IO will take more time and polling will take less time. Please tell me, did you understand? Is this point clear? So you can see this this very nice, this question I found this in this university. Okay, read this. In this university, I found this question, that interrupts are not always better than polling. Read this. That interrupts are not always better than polling. They are generally better than polling, but they are not always better than polling. Is this clear? Interrupts are not always better than polling. They are generally better than polling, but they are not always better than polling. Okay, I have given you the example. Okay, because of context switch, a lot of time will be wasted. Yes or no? Because of context switch. So this I've already told you. Very simple. Now let's move on. So tell me the answer for this question. This is Waterloo University question. Interrupt driven IO is always faster than programmed IO. This statement is false. Yes or no? Is this clear? Interrupt driven IO, that is always faster than programmed IO. This statement is a false. Okay, and the reason I already told you, because of interrupt, because of context switching, there is context switching in the interrupt. Because of context switching, the time can be wasted. Okay, is this clear? But remember, the interrupt driven IO, that is usually faster, that is generally faster. Now tell me, now what will be the answer? Now tell me what will be the answer. If I say that interrupt driven IO is generally faster than programmed IO, now tell me the answer. Now this statement will be true. Okay, interrupt driven IO, that is generally faster. Why this is generally faster? Tell me why this is generally faster. Tell me why this is generally faster? Because generally IO devices are slow. Yes or no? Because generally most IO devices are slow. Okay, is this clear? Because generally most IO devices are slow. Most IO devices, they are very slow. Are very slow. Is this clear? Please tell me. Let me know. So if IO device is fast, then who is better? Just tell me quickly. If the IO device is fast, then who is better? And if IO device is slow, then who is better? Okay. If IO device is fast, if IO device is fast, then programmed IO efficient. Then programmed IO efficient. Efficient. Okay, then programmed IO is efficient. And if the IO device is slow, then who is efficient? Then interrupt driven IO is efficient. Okay, and what is the general case here? IO device fast or IO device slow? Which is the general case? IO device fast or IO device slow? Which is the general case? IO device slow. Generally, IO devices are slow. Yes or no? This is the general case. Okay, generally IO devices are slow. Generally, most IO devices are slow. Or I can say very slow. Okay, so this is the general case, remember. So the generally interrupt driven IO is better. But if the IO device is fast, then programmed IO is efficient. So this is what we have seen. I hope you understood. So remember, interrupts are not always better than polling. Okay, if the IO device is fast, then polling is good. If the IO device is slow, then interrupt is good. And generally, IO devices are slow. So generally, IO devices, remember, generally, this, I can say interrupt driven IO, that is generally better. So in this question, you tell me, just tell me, in this question, we are saying, in this gate 1990 question, we are saying that programmed IO is faster than interrupt driven IO. That is false. Yes or no? Programmed IO faster than interrupt driven IO. This statement is false. But if I change, if I make it slower, now what about this? If I change this word and if I make it slower, now what will happen? Now what will happen? If I make it slower, now what will happen? Programmed IO is slower than interrupt driven. Programmed IO is slower than interrupt driven. This is also false. I told you. Yes or no? Because if the IO device is fast, then programmed IO will be better. Is this statement? So remember, programmed IO is faster. This statement is false. Programmed IO is slower. This statement is also false. But if I say generally slower, okay, generally slower. Now this statement will be true. Is this clear? Please tell me. So did you understand? So if you say that programmed IO is faster than interrupt driven IO, that is false. If you say interrupt driven IO is faster than programmed IO, that is also false. Because if your IO device is fast, then programmed IO is good. If IO device is slow, then interrupt driven IO is good. Generally, IO devices are very slow. So generally, interrupt driven IO is better. Okay. So very simple. Now let's solve this GATE 2005 question. A device with data transfer rate 10 kb per second is connected to a CPU. Data is transferred byte wise. Let the interrupt overhead be 4 microsecond. The byte transfer time between device interface and CPU or memory is negligible. What is the minimum performance gain? What is the minimum performance gain of operating the device under interrupt IO over programmed controlled mode? So this is a nice, beautiful question. Let's solve it. Let's understand this question word by word. First, what it is saying, it is saying that there is a IO device. Okay, there is a IO device with a data transfer rate of 10 kb per second. In 1 second, this IO device can transfer 10 kb. Okay, is this clear? So remember this IO device. What is the data transfer rate? Let me know. For this IO device that is given in the question, the IO device is sending the data transfer rate is given to you. Remember, the data transfer rate means this IO device, it can provide you 10 kb in 1 second. Okay, is this clear? In 1 second, it can provide you 10 kb. Understood? This is the first statement that this device can provide you 10 kb data in 1 second. Okay, this is connected to CPU. Data is transferred byte wise. Okay, the question is saying data is transferred byte wise. Let's see this. Data is transferred byte wise. What it means? Can anyone tell me? Byte wise. Anyone want to tell me what this statement means? Anyone who want to tell me what this statement means? Data is transferred byte wise. What this statement means? Tell me. Please tell me what this statement means. Data is transferred byte wise. See, this statement means that, see, IO device is sending the data to the interface. Do you agree? This IO device, this is very slow device. It is sending 10 kb data per second. Remember, per second. But remember, main memory and CPU, they are very fast. Main memory can transfer megabytes per second. CPU can transfer gigabytes per second. So IO device is actually very slow. Okay, remember. So this IO device will give data to whom? This will give data to interface. Yes or no? This is your interface. This is the interface. Okay, now remember this IO device will give the data to the interface. Now when 1 byte will be ready in the buffer, there is buffer in the interface. Yes or no? Now remember when 1 byte will be ready here, when 1 byte will be ready here, then it will be transferred to the CPU register. Then it will be transferred to the CPU register, and from there it will be transferred to main memory. Is this clear? Please tell me. Did you understand what this line means? Data is transferred byte wise. What this line means? Did you understand? Please tell me. See, the IO device is very slow. It is giving you 10 kb per second. Yes or no? So 1 byte it will give you in how much time? Tell me how much time 1 byte it will give you. Okay, 10 kb. To give you 10 kb, it is taking 1 second. Okay, to give you 1 byte, it will take how much time? It will give you, it will take 0.1 millisecond. Yes or no? Are you getting my point? See, 10 kb data you are getting in 1 second. So 1 byte you will get in how much time? You will get in divided by 10k. Okay, k means to the power 3. 10 to the power 3. So that means what? 1 byte data in how much time you are getting? 1 byte data you are getting in 0.1 millisecond. Okay, is this clear? So remember, this IO device is giving you 1 byte, 0.1 millisecond per byte. Okay, so very simple. Remember, this IO device is slow because this is giving you in 1 second, this is giving you only 10 KB. But remember, your CPU, your main memory, they are very fast. The main memory data transfer rate, that is megabytes per second. The CPU data transfer rate, that is gigabytes per second. Okay, so this slowly this IO device is giving you data. Now, when the 1 byte will come from the IO device to the buffer in the interface, this is your interface. Now, this is your IO interface. In the IO interface, when 1 byte will come, then what you will do? Then the CPU will take this byte and it will put it in the CPU register, and from the CPU register it will store it in the main memory. Is this clear? So who will do this? CPU will do this. Is this clear? By CPU. It will be done by CPU. It will be done by CPU. So CPU will take this data, this 1 byte data, CPU will take, it will put it in the CPU register. From there, it will store it in the main memory. So this is the idea. So this line is saying data is transferred byte wise, means when 1 byte will be ready, it will be transferred. When 1 byte will be ready, it will be transferred. Okay, is this clear? So very simple. Now the next line, let interrupt overhead be 4 microsecond. What this line means? Please tell me. Interrupt overhead, that is 4 microsecond. Okay, see. So see, the second information was data transferred byte-wise. Data transferred byte-wise. This was your second information in the question. Okay, the next information, what is that? Interrupt overhead. Interrupt overhead. That is 4 microsecond. Now, what this means? Can anyone tell me? What this means? Interrupt overhead is 4 microsecond. What this statement means? Read this statement and tell me what this means. Interrupt overhead is 4 microsecond. And remember, we are transferring data byte-wise. See, what this statement will mean, let me tell you. This statement is like this. From the IO device, 1 byte will come. This is your IO device. Okay, this will give you 1 byte. This will give you 1 byte. When the 1 byte will come to the interface, in the interface, when 1 byte will come, this is your interface. Now, remember, when 1 byte will be ready in the interface, then what will happen? This interface will send a interrupt signal. Yes or no? This will send a interrupt signal. The interrupt signal will go to the CPU. Okay, now what the CPU will do? Whatever CPU is doing, CPU is executing some program. This is what CPU is doing. Now, whatever CPU is doing, CPU will save this work. Okay, after saving this work, CPU will do the context switch and CPU will do this data transfer. CPU will take this data, it will put it in the CPU register. From the CPU register, it will put it in the main memory. Yes or no? So this is what CPU will do. So remember, to save this current work, okay, because CPU, when the CPU will receive the interrupt signal, CPU will save this work because CPU is doing something. CPU is executing some program, so CPU will save this work. After saving this work, CPU will do the context switch, okay, and CPU will do this data transfer. This data transfer will be done by CPU. So you can see that is the overhead. Yes or no? Saving this work and doing the context switch, that is the overhead, and that is your 4 microsecond. Tell me, this 4 microsecond happens for every byte, can I say? This 4 microsecond, can I say this will happen for every byte? Because for every byte, one interrupt signal will be generated. Because remember, data is transferred byte-wise. Please understand. Please understand, data is transferred byte-wise, means when 1 byte will be ready, then you will generate the interrupt signal. This interface, who will generate? Who will generate the interrupt signal? When 1 byte will be ready, then this interface will generate the interrupt signal. Okay, this interrupt signal will be generated. So you can easily see that for every byte, this overhead will happen. I can say for every byte, interrupt signal will be generated. Okay, and finally I can say for every byte, 4 microsecond will be wasted. Is this clear? 4 microsecond will be wasted for every byte. Tell me, so how many interrupt signals will be generated? Tell me, how many interrupt signals will be generated? For every byte, one interrupt signal will be generated. For every byte, one interrupt signal generated. Tell me, just tell me this point. There, how many interrupt signals will be generated in this question? For every byte, because you are transferring the data byte wise, so every byte, one interrupt signal will be generated, and you can easily see. So how many total? 10K, yes or no? Total 10K interrupt signals will be generated. 10K interrupt signals will be generated. INTR signals generated. INTR signals generated. Okay, is this clear? Is this clear? Let me know. So now let's see the next thing. The question is saying the byte transfer time, because remember you will transfer the byte. Do you agree? Do you agree? You will transfer the byte. The CPU will transfer the byte, because when the one byte will be ready, okay, when one byte will be ready, this one byte, when it will be ready in the interface, when this one byte will be ready, then what the CPU will do? Okay, then CPU will transfer it to a CPU register. Yes or no? CPU register. Then it will transfer it to main memory. So remember, very simple, when one byte will be ready, because the question is saying that we are transferring data byte wise. So when this one byte will be ready in the interface, then CPU will do this transfer. CPU will take this one byte, CPU will put this one byte here, then CPU will take this byte and CPU will put it in the main memory. Okay, so very simple. So remember, the question is saying byte transfer time between device interface register, this is your device interface register, and CPU or main memory, that is negligible. This is already given to you that this is negligible. This transfer time is negligible. Okay. Now the question is saying what the minimum performance gain if you use interrupt mode over programmed controlled mode. This is the question. So I hope you understood everything. Did you crystal clearly understand every statement in the question? Please tell me. In this question, every statement did you understand in a very crystal clear way? This is a beautiful question. Every statement you understand what this statement is saying, what this statement means. Okay, now let's solve this question. So you can easily see that. First, let's talk about interrupt mode. Okay, is this clear? Let's talk about interrupt mode. Interrupt mode. In the interrupt mode, you are transferring 10 KB data per second. Remember, this device is transferring 10 KB data per second. Now, in the interrupt mode, how much time will be wasted? Tell me, for 10 KB. You can, okay, for 10 KB, how much time will be wasted? Means, let me know. What are the minimum performance gain? So let's see. In the interrupt mode, you tell me how much time the CPU is going to waste. Means CPU will spend how much time? CPU spends how much time? Let me know. Okay. So tell me. First of all, you can see in the interrupt mode, I told you that 10K interrupts will be generated for 10 KB data. Yes or no? For 10 KB data, remember, for 10 KB data, remember, 10K interrupt signals will be generated. 10K interrupt signals will be generated. This we have already seen. Signals will be generated. Okay. So 10K interrupt signals will be generated, right? For 10 KB data, these many 10K interrupt signals are going to be generated. Okay. And you can see where the CPU will spend time. Can anyone tell me where the CPU will spend time? In the interrupt driven mode, where the CPU will be busy, where the CPU will spend time. So CPU will spend time in two things. What are those two things? One is interrupt overhead. Yes or no? Interrupt context switching overhead. Yes or no? Context switching overhead. So here the CPU will waste time. Also, the CPU will be involved here. Where? Tell me. I am asking where the CPU will be involved in the interrupt driven mode. In the interrupt driven mode, CPU will be involved in the interrupt overhead, also in the data transfer. Yes or no? Also in the data transfer from IO to main memory, this data transfer. Correct? In these two things, the CPU will be busy. Do you agree with me? In the interrupt mode, CPU will be involved in two things. Okay, CPU will be involved in two things. One is this context switch, or I can say interrupt overhead. Okay, because you need to save your work, you need to do context switch. So that is the overhead. So there CPU will waste some time. Also, the CPU has to do the actual transfer. Once 1 KB will be ready in the interface, 1 KB will be ready. Sorry, 1 byte will be ready. okay, in the device interface, 1 byte will be ready. Then CPU will do the data transfer. Do you agree with me? Who will do the data transfer? When 1 byte will be ready in the interface, then who will do the data transfer? CPU will do the data transfer, right? Yes or no? So CPU will be involved in these two things, interrupt overhead and also this actual data transfer. The question is saying actual data transfer is zero. Yes or no? The question is saying actual data transfer is zero. Now we only need to see what will be interrupt overhead, because the question is saying the actual data transfer time is negligible. Okay, see this. The byte transfer time between CPU device and main memory, that is negligible. Okay, so you can see this time is already zero. Now let's focus on the interrupt overhead. So what is the interrupt overhead time? What is the interrupt overhead time? What that will be? Very simple. That for every byte, 4 microsecond will be wasted. Yes or no? For every byte, 4 microsecond will be wasted. So you need to, if you are transferring 10 KB data, see, the question is not saying that you are transferring 10 KB data. Remember, is the question saying you are transferring 10 KB data? Is the question talking about transferring 10 KB data? No. See, the question has given the data transfer rate, that is 10 KB. This is a general statement that data transfer rate of device is 10 KB. But the question is not saying that you are transferring 10 KB data. Okay, so this question you can solve from 10 KB point of view, or you can solve from 1 byte point of view. Okay, is this clear? What I'm saying in the question is not saying how much data you are transferring. The question is saying that data transfer rate of the device is 10 KB per second. This device can give you 10 KB per second, but the question is not saying how much data we need to transfer. So this question you can solve, either you can solve from 1 byte point of view. Okay, is this clear? You can solve this question from 1 byte point of view. You can solve this question from 1 byte point of view, or you can solve this question from 10 KB point of view, no problem. Is this clear what I'm saying? Did you understand this point? Did you understand? See, the question is not saying how much data we need to transfer. Read this. The question is not saying how much data we need to transfer. The question is just saying that the data transfer rate of device is 10 KB per second. This device can give you 10 KB data per second. Okay, but we don't know how much data we need to transfer. So to solve this question, okay, minimum performance gain, and to solve this question, remember, you can either use 1 byte point of view, or you can solve this question from 10 KB point of view. Let me solve it from both. Okay, let me solve it from both point of view. So tell me, so for 10 KB data, tell me how much time will be wasted. Let me solve from 10 KB point of view. Means I am assume we need to transfer 10 KB data. Assume we transfer 10 KB data. Okay, just assume that we are transferring 10 KB data. Okay, so from the 10 KB point of view, tell me what will be the answer. Very simple. Okay, for every byte, 4 microsecond will be wasted. So this much amount of time CPU will be CPU will be wasting. CPU will be spending this much amount of time. Agree? Correct? Okay, is this clear? Because for every byte, 4 microsecond will be wasted, and assume we are transferring 10 KB data. So for 10 KB data, 10K multiplied by 4 microsecond, this much amount of time CPU will be spending. Okay, clear? Yes or no? From 1 byte point of view, how much? Assume we transfer 1 byte. Assume we transfer 1 byte only. So tell me, from 1 byte point of view, what will be the answer? For 1 byte only 4 microsecond. Yes or no? Okay, for 1 byte only 4 microsecond. For 1 byte only one interrupt signal will be generated, because we are transferring data byte wise. So for 1 byte only one interrupt signal will be generated. So only 4 microsecond will be wasted. Yes or no? Correct? Okay. Now let's see about the programmed IO. What about the programmed IO? You tell me about programmed IO. How much time the CPU will spend if you are using programmed IO, and let's assume you are transferring 10 KB data. Assume we transfer 10 KB data. Tell me, then in the programmed IO, how much time will be spent? How much time CPU will spend? Please tell me. Because assume we are transferring 10 KB data. We need to transfer 10 KB data. We need to transfer 10 KB data. Then in the programmed IO, The CPU will be involved where? CPU will be involved whole time, yes or no? CPU involved whole time. Do you agree? CPU will be involved whole time. Either CPU will be transferring this data from IO device to main memory, or the CPU will be checking the status register. Yes or no? Is this clear? So CPU will be involved whole time. Whole time CPU will be involved. So if you want to transfer 10 KB data, then already this is given that 10 KB data, for that you need 1 second. Yes or no? Is this clear? And remember, in the programmed IO, there is no interrupt. There is no interrupt overhead. There is no interrupt signal. There is no interrupt. Okay, is this clear? So remember, for 10 KB data, if you want to transfer 10 KB data, then how much time you need? If you want to transfer 10 KB data, for 10 KB data, how much time you need? Only 1 second. The question is saying that you can transfer 10 KB in 1 second. So for 1 second, for the entire time, CPU will be busy. CPU will be involved all the time. So 1 second, for 1 second, CPU will be busy. Is this clear? For 1 second, whole time CPU will be busy. CPU involved. Okay, is this clear? What about 1 byte? Tell me, what about 1 byte? If I want to transfer only 1 byte, then tell me, if I want to transfer only 1 byte data, then what about this? Very simple. You can calculate 1 byte data means 1 byte data you can transfer in how much time? That will be 1 divided by 10k seconds. Okay, so that is going to be your 0.1 millisecond. Okay, is this clear? Because remember, in the programmed IO, there is no interrupt. There is no interrupt. Okay, so you can easily see that for 1 byte data, this much amount of time, because 10 KB means 1 second. Okay, if you want to transfer 10 KB data, then 1 second it will take. Okay, and the CPU will be involved all the time. CPU is involved all the time. Okay, is this clear? So that is the reason, for 1 byte, this much amount of time CPU will be busy. Okay, is this clear? Let me know. So CPU busy. This is the CPU time taken. This is the CPU time taken. So very simple. I hope you understood this. Now the question is saying what the performance gain. Correct? What the question is saying. See, the question is saying what the performance gain using interrupt over programmed controlled IO. Okay, now this question you can easily solve. So now I am solving this question actually using two assumptions. See, remember the first assumption, assume you need to transfer 10 KB data. 10 KB data needs to be transferred. Needs to be transferred. Okay, in this situation, how much time in case of interrupt driven, how much time CPU will take? Tell me. In case of interrupt mode, how much time CPU will take? And in case of programmed mode, how much time CPU will take? Tell me. In this case, how much time CPU spends how much time? And here CPU spends how much time? Tell me quickly. For 10 KB data, okay, in the interrupt mode, CPU spends how much time? That was your, for 10 KB data, 4 microsecond. Yes or no? 10 multiplied by 10k multiplied by 4 microsecond. Correct? This was the answer. And here in the programmed mode, all the time CPU will be spending. So 1 second. Okay, correct. Now the final answer will be what? The final answer. We need to see what the speed up. Basically, we need to see what the speed up. We need to see what is the speed up. So let me tell you, this is the idea that if someone asks you what the speed up means performance gain. If someone asks you speed up of A over B, okay, if someone asks you speed up of A over B, then it simply means that, what it means, speed up of A over B, it means execution time of, here we want to know speed up of A over B. Here execution time of B divided by execution time of A. Execution time of B divided by execution time of A. This is the formula. Is this clear? Let me know. See, Very simple. Just think about it. Let's assume that interrupt mode is spending only 50 seconds and this is spending 100 seconds. Then how much speed up we are getting in the interrupt mode? Just think about it. I am asking. Let's assume interrupt mode we are spending 50 seconds. In this mode we are spending 100 seconds. Then how much speed up we are getting? How much speed up we are getting in the interrupt mode? Double, yes or no? Because we are spending half time. Do you agree with me? We are spending half time, so speed up is double. Do you agree? Please tell me. If if interrupt mode is spending 50 seconds and programmed mode is spending 100 seconds, then it means how much speed up we are getting using interrupt mode? That will be two times. Okay, yes or no? Because interrupt mode is taking half time than programmed mode, so the speed up will be double. Is this clear? So the speed up will be double. So this is what I'm saying. Remember, if someone asks you speed up of A over B, then that will be execution time of B divided by execution time of A. Okay, so here the same thing. What is the speed up? Here also the same thing. What is the speed up of interrupt mode? Interrupt mode. What is the speed up of interrupt mode over programmed mode? What will be the answer? What is the speed up of interrupt mode over programmed mode? What will be the answer? Answer will be how much time CPU is spending in the programmed mode, that is 1 second. Yes or no? How much time CPU is spending in the programmed mode, that is 1 second, divided by 10K multiplied by 40 microsecond. What is the answer? Can you tell me? Second cancel. What it will be? It will be micro means 10 power 6. Okay, so it will become 10 power 6 divided by 10 into 10 power 3. So what that will be? And that will be 4 also. Okay, so that is going to be 100 divided by 4. So that is 25. This is not percentage. This is 25. That's it. 25 times means what I'm saying? I'm saying that 25 times this is better. Okay, this is better 25 times than this. Interrupt mode is 25 times better than programmed mode. Is this clear? This is not percentage. This is times, means interrupt mode is 25 times better than programmed mode. Is this clear? So the answer will be 25. Means what it means? It means interrupt mode. Okay, in this question, interrupt mode is 25 times better than programmed mode. Okay, so this is 25 times. This is not percentage. This is not 25%. This is 25 times. That interrupt mode is 25 times better than programmed mode. Okay, is this clear? Now I told you that same question you can solve from 1 KB point of view, from 1 byte point of view also. The same question you can solve from 1 byte point of view also. So let's solve it from 1 byte point of view. Okay, from 1 byte point of view, let's solve it. So tell me, if you want to transfer 1 byte data, then in the interrupt mode, how much time CPU will spend? That is 4 microsecond, already given in the question. Okay, for 1 byte, 1 interrupt signal will be generated. So for 1 byte, 4 microsecond, this is the interrupt overhead. Okay, is this clear? So this is CPU will spend 4 microsecond. And for 1 byte, this micro programmed mode, this will spend how much time? This is 0.1 millisecond. We have already calculated. So finally answer will be what? Speed up. Speed up of interrupt mode over programmed mode. What that will be? What the answer will be? The answer will be, you can easily see how much time we are spending in the programmed mode, millisecond, divided by 4 microsecond. Can you calculate this? Tell me. So it will be 0.1 multiplied by 10 to the power minus 3 divided by 4 10 to the power minus 6. So what it will become? It will become 100 divided by 4. So that is 25. Again 25 times. Okay, is this clear? So whatever method you apply, the answer will be 25. Is this clear? So interrupt mode, in this question, interrupt mode is 25 times better than programmed mode. So whatever method you apply, you will get the same answer. Did you notice one thing in the question? See, the question is not talking how much data we need to transfer. Do you agree? The question is not saying how much data we need to transfer. Yes or no? The question is not saying how much data we need to transfer. Okay, the question is simply saying that this device has transfer rate of 10 kb per second, means this device is transferring 10 kb data per second, but the question is not saying how much data we need to transfer. So remember, this question you can solve from 10 kb point of view, or you can solve it from 1 byte point of view. You will get your answer. Okay, it is your choice. You can solve it from 1 byte point of view, you can solve it from 10 kb point of view. In both the situations, you will get your answer. You will get 25 times. Is this clear? Let me know. Please tell me. So you can solve this question from 1 byte point of view, or you can solve this question from 10 kb point of view. That is your choice. You will get your answer, that is 25. Let's solve this question. This is GATE 2023 question. A keyboard connected to a computer is used at a rate of 1 key stroke per second. Means in 1 second you will press one button. Okay. So let's solve this question one by one, step by step. Read the question. The question is saying that there is a keyboard connected to computer, and what we are doing, the data transfer rate of keyboard, that is per second 1 key stroke. Okay, is this clear? What we are doing, we are pressing one key stroke per second. Okay, one key stroke per second. Now the next, the computer system polls. Okay, the question is saying the computer system polls, means programmed IO. Okay, we are using the programmed IO. The computer system polls the keyboard every 10 millisecond. Means every 10 millisecond, one poll will be this CPU will poll one time. Basically, this CPU will check the status register. Yes or no? In this keyboard interface, there is a status register in this keyboard interface. Okay, so very simple. There is a keyboard interface. Let's assume this is the keyboard interface. In the keyboard interface, what we have, there is a status register, that also you know. There is a status register. Okay, in the status register we have a status bit. This bit is there. So in the polling method, what the CPU will do, CPU will check this bit every 10 millisecond. The CPU is checking, is this bit ready, is the data ready, is the data ready, is the data ready. Okay, yes or no? So you can easily see the CPU, what the CPU is doing. Notice the CPU, what this is doing, this is checking this bit. This is checking bit that one once every 10 milliseconds. Okay, is this clear? This is what the question is saying, that we are polling the keyboard. We are polling the keyboard, means is the data ready, is the data ready. Okay, did you press the key, did you press the key, did you press the key? So we are polling every 10 millisecond. We are polling to check whether the key has been pressed. Okay, whether there is a key stroke. Okay, is this clear? So you can see once every 10 millisecond we are polling, we are checking this bit. Basically, the CPU is continuously checking this bit. Okay, so every 10 millisecond, one time we are checking this bit. Okay, to check whether data is ready or not, to check whether someone has pressed the keyboard or not. Okay, and it will consume 100 microsecond for each poll. Okay, remember, every 10 millisecond we are checking it. Okay, and when we check it, then actually what happens, see, I told you that once every 10 millisecond, what we will do, the CPU will check this bit. CPU will check this bit. Now let me tell you, for checking this bit, what will happen? For checking this bit will go to CPU. Yes or no? Via data bus. Okay. When you are checking this bit, then remember this bit will go to the CPU via data bus. Actually, this status register will go to the CPU. Okay, via data bus. Via data bus, this status register will go to the CPU. So let me tell you, the status register, this status register will go to the CPU via data bus. Now the CPU will have the status register. Okay, and the CPU will check this bit. Is this clear? CPU will check this bit. CPU checks. Okay, is this clear? So this time, basically, this time is 100 microsecond. Is this clear? So the question is saying that 100 microsecond for every poll. Okay, for every poll. Is this clear? For every poll, 100 microsecond will be wasted. Did you understand why for every poll 100 microsecond is wasted? Because remember, CPU is checking this register every 10 millisecond. Means after 10 millisecond, CPU will check it. Then again after 10 millisecond, CPU will check it. Then again after 10 millisecond, the CPU will check it. Now, how the CPU will check this? So what the CPU will do? This status register will go to the CPU via data bus. Okay, and then the CPU will check this bit, whether this bit is 0 or 1. Okay, means if this bit is 1, it means someone has pressed the key, okay, on the keyboard. If this bit is 0, means so far the key has not been pressed. Okay, so you can see that for this, for every poll, 100 microsecond is wasted. Okay, 100 microsecond is wasted to check this key. Basically 100 microsecond is wasted to check this status register. This is what I am saying. Okay, next, let's see the next. If it is determined, read this. If it is determined after polling that key has been pressed, okay, means if this bit is 1, if this bit is 1, then it means that key has been pressed. So you can see, if it is determined after polling that the key has been pressed, then CPU will consume additional 200 microsecond to press the keystroke. Okay, see, when the CPU will know that this bit is 1, when the CPU will find out that keystroke has been pressed, key has been pressed, then what the CPU will do? Tell me, can anyone tell me? In the polling method, when the CPU will find out that key has been pressed, means this status bit is 1, then what the CPU will do? Then CPU will take this key. Okay, yes or no? In the data register there is key, the key that you are pressing. You are pressing some key. Let's assume you are pressing some key, maybe key number Y. Okay, you are pressing key button, Y button you are pressing. Then here, this data CPU will put it in the main memory. Yes or no? This data will go to the CPU. CPU will take this data, and from the CPU register, this data will go to the main memory. Very simple. Okay, so for that, 200 microsecond will be consumed. Okay, is this clear? Now the question is saying, let T1 denote the fraction of a second. How much part of a second is spent in polling and processing the keystroke? This is what the question is saying. Okay, see, very simple question. What is T1? T1 is basically, we are using the polling method. Remember, what we are doing, we are using the polling method. This polling IO method we are using. Okay, and the question is saying that what is T1? T1 is time, fraction of second, means how much fraction of second, fraction of 1 second spent in spent in polling, spent in polling and processing key. Okay, processing keystroke. So this is what the question is saying. Now notice one thing. So tell me, in polling how much time will be wasted? Fraction of 1 second. Okay, you look at 1 second. In 1 second, how much time? In this 1 second, there is one, this is 1 second. In this 1 second, how much time will be spent in polling? In 1 second, how much time will be spent in polling? Can anyone tell me? During this 1 second, how much time will be spent in polling? Notice what will happen. This is your 1 second, correct? Okay, so remember, every 10 millisecond, okay, after every 10 millisecond, how much time you are wasting? Remember, this is your entire thing is 1 second. This is entire thing. Now I am saying that after 10 millisecond, after 10 millisecond, what we will do? After 10 millisecond, we will do the polling. So here we will do the polling. Do you agree? Here we will do the poll. Okay, and for this poll, how much time? The question is already saying that for this poll, 100 microsecond will be spent. 100 microsecond for each poll. This is given in the question. Read this. 100 microsecond for every poll. So notice that this is 1 second. This entire thing is 1 second. Now, after 10 millisecond, we will do the poll. Remember what we are doing? We are doing the poll after 10 millisecond. So here we are doing the poll. And for poll, how much time? 100 microsecond for every poll. Okay, so 100 microsecond for this poll. Okay, for each poll, remember, for each poll. Okay, now again what will happen? Again what will happen? After again 10 millisecond, what will happen? Tell me. After 10 millisecond, again what you will do? Again you will poll. Again you will poll. And again how much time will be spent? 100 microsecond. Yes or no? Tell me, when the key will be pressed, the question is already saying when the key will be pressed. When the key will be pressed, the question is saying one key is pressed per second. See this. The question is already saying that in 1 second, one key will be pressed. 1 second, one key will be pressed. Is this clear? The question is saying that in 1 second, one key will be pressed. 1 second, one key will be pressed. Okay, so can I assume that here key will be pressed because this is 1 second. This entire thing is 1 second. Okay, so can I assume here key will be pressed? Can I assume? Please tell me. Let me know. So can I say that in 1 second, one key will be pressed? Yes or no? This is your 1 second time. In this 1 second time, one key will be pressed. Okay, so you can see the key will be pressed here at this point. At this point, the key will be pressed. Okay, and until then, key is not pressed. Yes or no? Until then, what will happen? After every 10 millisecond, this is the next 10 millisecond. Remember, okay, this is the next 10 millisecond. After this 10 millisecond, again, what we will do? Again, we will do poll. In this poll, again, 100 microsecond will be wasted, and so on. So tell me how many times you will do this poll? Tell me how many times you will do this poll, means how many times we are going to do this poll. Can anyone tell me? Here. Okay, how many times we will do this poll? Let me know. So very simple. How many times we will poll? Let's solve it. How many times? In a second. In a second, we will poll. The answer is very simple. Remember, in 10 millisecond, you are polling one time. 10 millisecond, one poll. Yes or no? Agree? This is given in the question that 10 millisecond, one poll. Okay. So in 1 second, how many polls? In 10 millisecond, one poll. So in 1 second, how many polls? That will be 1 divided by 10 milli polls. Okay. That is same as milli means 10 to the power minus 3. Okay. So it will become 100 polls. Can I say that there will be total 100 polls? So how many times in a second we will poll? Within a second, how many times we will poll? That is 100 polls will be there. Correct? Yes or no? 100 polls will be there. So remember, in this polling, total 100 polls. In every poll, how much time is wasted? Total 100 polls multiplied by how much time wasted in every poll? That is 100 microsecond. So this is the time wasted in polling. This is the time wasted in polling. Okay, is this clear? And to process the keystroke, because in 1 second, one keystroke will be pressed. Yes or no? So per second, one keystroke will be pressed. Yes or no? So how much time will be wasted? Processing keystroke. Remember, in 1 second, one key will be pressed. One key will be pressed. Okay, so in 1 second, you tell me how much time will be spent in 1 second. How much time will be spent in processing? That is already given. That is 200 microsecond. Okay, spent in processing. Spent in processing. 200 microsecond, that is given in the question. You can easily see that the question is already saying 200 microsecond to process the keystroke. Read this. Additional 200 microsecond to process the keystroke. Okay, is this clear? Now remember, the question is asking per second. The question is asking per second. So per second, how much time will be wasted? Per second, how much time will be wasted in the program, in the polled IO, in the polling IO mode? Tell me. In the polling IO mode, what is T1? T1 is equal to time spent on polling. Yes or no? Polling time polling time plus processing time plus processing time. Yes or no? Polling time plus processing time per second. Per second. Okay, per second. So what is the polling time that we already found? So total 100 polls are there. There are total 100 polls multiplied by 100 microsecond plus processing time is 200 microsecond. So what is the answer? From here, what answer you got? How many microseconds you got? That will be 100. That will be 10,000, 1200. Yes or no? That will be 10,000, 1200. 200. 10,200. These many microseconds. Is this clear? Please tell me. Is this clear? 10,200 microseconds. So this is your T1. We found the T1. Remember, we got the T1. Now let's see T2. Now let's focus on T2. Okay. For T2, we are using interrupt mode. Interrupt mode. For T2, we are using interrupt mode. Okay. So what is T2? Now let's see this. So let's focus on T2 now. Now what will be T2? Okay, so read this. Now the question is saying, in an alternative implementation, the system is using interrupt instead of polling. The system is using interrupt instead of polling. An interrupt is raised every keystroke. The question is saying an interrupt is raised for every keystroke. For every keystroke, interrupt is raised. Is this clear? For every keystroke, for every keystroke, one interrupt is raised, right? One interrupt raised. For every keystroke, one interrupt is raised. Now, the question is saying it takes a total of 1 millisecond for servicing the interrupt and processing the keystroke. To service the interrupt and to process the keystroke, 1 millisecond will be taken. Basically, one interrupt means one interrupt means 1 millisecond. One interrupt means 1 millisecond time. Okay, is this clear? One interrupt takes 1 millisecond time. One interrupt takes 1 millisecond time. Okay, is this clear? Now the question is saying T2 is denoting the fraction of second spent in servicing the interrupt and processing the keystroke. Okay, so tell me, every second how many interrupts will be generated? Every second how many interrupts will be generated? Tell me, every second how many interrupts will be generated? See, the question is saying that per second one keystroke we are pressing. Already the question is saying, notice. Already the question is saying that in 1 second, we are pressing one key. One key is pressed. This is already given in the question that in 1 second, one key is pressed. Okay. So, and in 1 second, if one key is pressed, then in 1 second, I can say one interrupt will be generated. Correct? One interrupt will be raised. Okay, yes or no? So in 1 second, if one interrupt is raised, then in 1 second, only 1 millisecond time will be wasted. So this is T2. So your T2 will be 1 millisecond only. That's it. Your T2 will be 1 millisecond only. Because remember, already the question is saying, read this question. The question is already saying that per second we are pressing one button. Okay, one button we are pressing per second. Now what is T2? T2 is fraction of 1 second. Okay, in 1 second, how much time the interrupt will take? Okay, how much time will be taken for servicing the interrupt and processing the keystroke? That is 1 millisecond. Because the question is already saying that every key, for every key we will raise one interrupt. Yes or no? So remember, in 1 second one key will be pressed. For one key one interrupt will be raised. So in 1 second one interrupt will be raised, and for one interrupt you need one millisecond. So that's it. T2 equal to 1 millisecond. So we got T2, that is 1 millisecond, and we got T1, what was T1? That was 10,200 microsecond. Okay, now the question is asking, what is T1 T2 ratio? T1 divided by T2. The question is saying what is T1 divided by T2. So T1 is 1 millisecond. Milli means 10 to the power minus 3 second, divided by what is T2, that is 10. These micro means 10 to the power minus 6 second. So now what it will become? It will become 1000 divided by this value. Can anyone tell me what is this value? Can you take a calculator and tell me what is this value? Rounded off to one decimal. Rounded off to one decimal. So anyone want to tell me what is this value? This is 10 divided by 102. 10 divided by 102. What is that? Take calculator and tell me quickly. 10 divided by 102. So let me calculate. So this value will be 0.098, something like this. Okay, the question is saying that rounded off to one decimal place. So what the answer will be? Rounded off to one decimal place. So here the answer will be what? Sorry, we made a mistake, right? Because the question is asking T1 divided by T2, and we have done T2 divided by T1. Let's do T1 divided by T2. So the question is asking T1 divided by T2. What is T1? T1 is these many microseconds, and T2, that is 1 millisecond. So the answer will be what? That is these micro means 10 to the power minus 6 divided by 10 to the power minus 3. So that is going to be divided by 1000, and that is your 10.2. Yes or no? 10.200. This is the answer. The question is saying that rounded off to one decimal place, so that will be 10.2. So the final answer will be 10.2. Okay, the question is saying rounded off to one decimal place, the answer will be 10.2. So very simple question. Is this clear? So we have done this GATE 2023 question. This is very simple question and very nice question. So the answer will be 10.2. Okay. Now I told you that interrupts are general concept. We have already seen interrupt driven IO for data transfer. If you want to do data transfer between IO and main memory, then we have already seen this interrupt driven method. But interrupts are general concept, remember. Okay, using interrupts, you can do data transfer. Also, you can do many other things. So we need to study the general concept of interrupt. Yes or no? Now, so far we have seen interrupt driven IO for data transfer. Now, next we will study interrupts in general. Now we will study interrupt processing in general. So this is our next topic, that is interrupts, or I can say interrupt processing in general. Okay. So thank you everyone. Please let me know, did you understand all the questions? Did you understand programmed IO and interrupt driven IO? Did you understand in a crystal clear way? So we have seen what is programmed IO, what is interrupt driven IO for data transfer. We want to do data transfer between IO device and main memory. So this is what we have seen so far. Okay. And we have seen the differences of programmed IO and interrupt driven IO. What are the differences? Who is better? Okay. If the IO device is fast, then programmed IO is better. If the IO device is slow, then interrupt driven IO is better. Usually, in most of the cases, IO device is very slow. So interrupt driven IO, that is generally faster than programmed IO. So all these concepts we have seen, and then we have solved some gate exam questions, and some standard questions we have done. Okay. So please let me know, did you crystal clearly understand every concept? Is every concept crystal clear in your mind? Can you visualize and can you solve every question in a very clear, correct, and complete way? Okay, so please share your feedback in the comments. Let me know. Okay, thank you everyone.